Okay, so a few words on, this is rather loud, no? A few words on my bio. I spent 8 years developing enterprise software, both serial and parallel versions that are still used by hardware engineers to manufacture and test their chips. So chances are the chips in your laptop or cell phones were designed with that software in mind. And since 2006, I've been on my own self-funded engineer, CTO. We have a complete SPM Python, which is a distribution for high-performance parallelism, and a consulting angle. So anyway, a footnote on the topic, on this general term of exploiting parallelism before I go to the main topic. And that is this. This is the year 2013. Okay? This is a field that is at least 60 years old, 60. And yet there is no consensus on what this means across the open source, academic, and commercial world. So if you gather 5 experts and you ask them, well, what does this mean? You're not going to end up with 1 or 5 answers. You're going to end up with 30, 40 answers. I can't think of any other field that is 60, 70 years old that has this issue. It's really damning. So in light of that, what I'm about to say, you may by all means consider it suppositions on my part. Totally fine with me. We'll be making quite a few very strong claims. So, okay, now the topic at hand. Now I'm sure all of us have come across some version of this plot. And what I have here on the x-axis is the size of input, which can take one of several forms: data, graphs, and matrices, sparse and dense. And then on the x-axis, of course, there is time. And this is the situation that we face. It's basically growing on us, right? So far, no surprises. Things to note about this slide, specifically things that are not mentioned. There's no reference to big data. There's no reference to smart data. There's no reference to data with depth. And just to pick on big data, if what we face can be attributed to big data, my question is, what are we going to call it tomorrow? Huge data? And then what? Humongous data? So I, for one, am not interested in tracking this nomenclature. There are enough real problems here that we don't need a buzzword-centric take on things. So the real question is, what are we going to do in response to this? That's where things get very interesting. So let's come up with an answer. It turns out the answer can actually fit on a single slide. The essence of the solution will work no matter where you are along the plot. Tens of megabytes, gigabytes, terabytes, makes no difference. And we're going to derive that answer through a series of transformations. And to start that off, let's imagine that we are in the recent past, where this was a typical situation. Where we will be invoking some serial module. It will be CPU bounded. The emphasis here is on parallelism, not concurrency. How many of us have heard of those two terms, parallelism and concurrency? People misuse them, so I just want to emphasize that it's parallelism, not concurrency. So we have a serial module, and we were invoking it, and then after some time, we would have realized that wouldn't it be nice if we could invoke multiple instances of the serial module with different parameters, for example. And so we would essentially like to do something like this. We would like to have multiple invocations of a serial module. Now, just like in life, anytime you have multiple things going on, there must be a notion of a manager. So the first thing we have to do when we have this kind of a situation is we have to answer the question, how are we going to manage the execution of these things? What does it mean to successfully finish? How do we handle premature terminations? What is the fault tolerance policy? How are we going to handle deadlocks? If we have answers for those things, the resulting software is going to be really robust. If we don't, there is a price to be paid. And it's fairly hefty. It doesn't really matter which language we use. It is what it is. Okay, so now there are various ways of answering this question of how we manage this. We could write a documentation that says when you launch these jobs, use this script. When it finishes, use this other script, and on it goes. Or we could have a website that shows us the jobs that are submitted, that are running, that are finished. Or we could hook it up to an email system that says, oh, this job is still running. Or we could have a hack, which basically pings the system saying, I submitted 2 jobs an hour ago, are they done yet? Are they done yet? Are they done yet? What if we could actually write a parallel module, an honest-to-goodness software that just works? Now, if we could do that, then all of a sudden, we can invoke these multiple modules. We don't have to second guess. We don't have to check our emails. We don't have to check the website. I can tell the module saying, I don't care when you start, finish by 8 o'clock tomorrow morning. It will finish. What if we could write that? So imagine a world where that is possible. This carries on for some time until someday we realize we would like to have multiple invocations of the parallel module itself. Our system is getting larger. And just like before, whenever you have multiple things going on, you have to answer the question, how are you going to manage those executions? And just like before, you have choice. You can have documentation, you can have a website, you can have a hack, or how about if we write a program, an honest-to-goodness program that allows us to exactly describe what this parallel workflow is going to be, and it will always work. It will never hang. This carries on until one day we realize that our competition is solving a problem that uses only 10 machines. And we are using 1,000 machines for the same problem. So we have an issue now. How are they able to get away with only 10 machines? So we are going to now go into our workflow and come up with various versions of various capabilities. So instead of using a GPU, we'll use something else. And in other words, we have various incarnations of our workflows. And the story repeats again. Whenever you have multiple things, you must answer, how are you going to manage? So to tie this to today's presentation, we are going to have 3 forms of parallelism, which means that we have 3 ways by which to manage resources. Okay? Now, this is the part of the story where we can't go any further until we define what parallelism is, notwithstanding the footnote. So, but before we get to the footnote, I want to, how do we write this parallel module? How do we write this parallel workflow that it just works? We need some guiding principles that kind of help us along the way. And this is the most powerful quote that I can think of. It's really profound. I can't say enough good things about it. It's by Benjamin Wolff, who said, a language determines the concepts we can think of. Now, this was in the context of, he's a linguist, or was a linguist. So this is in the context of languages, human languages. Now, when he made this statement, it was fairly controversial. I don't understand the controversy, because anybody who's been taught multiple languages from childhood knows that there are certain languages that are really good at something and not others. So we'll take this as a given. Languages determine the concepts we can think of, especially for parallelism. Boy, does it make a difference. But we have to augment it for our situation. So we're going to say, it's not just a language that determines the concepts we can think of. Runtime environments determine the concepts we can think of. Parallel frameworks determine the concepts we can think of. And so do parallel libraries. They all bring unique set of vocabularies to the table that allow us to express parallelism. If they're too restrictive, we have to twist our way 20 ways from here to Sunday to express an obvious idea. If it's too much freedom, we're going to be overwhelmed with too many choices. So this vocabulary has to be just right, and that matters. Okay, so before we define parallelism now that we have the big structure, homage to a frequently asked question on the web on this topic of parallelism, and that is this: is exploiting parallelism easy or hard? Right? Now, I don't have a blog, but if I were interested in having a blog and generating a lot of traffic with the least amount of effort, given that I'm fairly lazy, all I have to do is answer this question. Pose the question, answer it, sprinkle it at Hacker News and a couple of other places, and hordes of people will show up. There's something about this question that just attracts people. And yet I'm not a fan of this question because it's an absolutely toxic question. And the reason is, somebody were to pose this question to me, I just have to say yes or no. I don't have to bother to justify my answer. And so what ends up happening is there are dime a dozen opinions on this, and therefore a lot of noise. However, I'm fascinated by this question, because we know from situations, on our own experience, there are situations where parallelism is extremely easy. Even if it involved 2 machines, who cares? It was easy. And then in the rest of the situations, man, it's so painful. Now the question is, why is that the case? To what can we attribute this degree of difficulty to? Right? In today's tutorial, we're going to talk about 3 forms of parallelism. Why 3? How should you decide which one to pick? And And turns out that the essence, now I'm not claiming that if you answer this question, we have solved all our problems. What I'm claiming is that it helps us establish constraints within which we have to operate. So the other engineering fields, the electrical engineers and the structural engineers, they have a nature to keep them honest because they have physical laws that they have to follow. With software engineering, it seems like anything can go. This is like an analogy to that. We have to follow these guiding principles. So what's the answer? Why is it something difficult and something so easy? Everything has to do with one simple thing, which is the gap between the intent and the API or parallel enabling technologies. If the gap is large, the project is going to be tough. It doesn't matter what language you use, it doesn't matter what the infrastructure you have. If the gap is small, it's going to be a piece of cake. So if somebody were to tell, for example, consider an analogy. If somebody were to tell me to build a wall somewhere here, I could build it 1 grain of sand and clay and cement at a time. And just thinking about it gives me a headache. Or I could take a break and say, I'm going to introduce a notion of a brick. I'm going to use bricks to build a wall. Now, what is the difference between the API of the brick and the API of a grain of sand? The API of the brick is closer to us in the context of this wall. That's why it makes us efficient. The API of the grain of sand is much further out. So if we have a gap, that gap has to be reached by us, the software engineers or the domain experts, not the provider of the brick and not the provider of the grain of sand. It's our responsibility to bridge that gap. So the moral here is we want to always, so the essence of tying back to the solution here is talking about the vocabulary. If I'm thinking in terms of MapReduce, I want the runtime environment to give me the ability to express MapReduce. If I'm thinking in terms of a list of tasks, I want the same environment to give me the ability to express a list of tasks. I don't want to find myself in a situation where I'm thinking in terms of A and the system only provides me B, and then I have to kind of map my way from A to B. If I'm thinking in terms of a template, the system has to allow me to express the notion of a template. That's the only way we'll be productive with parallelism. There's no other shortcut. So if that is the case, then the natural question is, well, how many types of PETs are there? Seems like it's very important. It kind of determines whether we are going to be successful on a particular project or not. One side note, the most important attribute anybody can bring to the table here when working in this space is knowing what to avoid. There are simply too many choices here. Right? That's the most important attribute. Whether you're a domain expert or a software engineer, you need to know what to avoid. So what are the, sorry, yes? And I'll get you in the very next slide, the one that I was about to click to. Yeah. Okay, so the PETs now. How many types of PETs are there? Because they determine how far off we are from our notion of parallelism. There are 3 kinds. The first ones are libraries. So you have OpenMPIs, OpenMPs, and the CUDAs of the world. They come at us from the perspective of the respective hardware systems. So OpenMPI was created 20 plus years ago to express parallelism across servers. OpenMP came about because of the need to express parallelism inside a node or inside a server using only control-centric nodes or control-centric threads or cores. CUDA came about because of the need to express parallelism inside NVIDIA's GPU cards. They are all coming at us from the respective hardware systems. Meanwhile, we are coming at the same problem from the other direction, with the perspective of a particular problem. That gap has to be bridged, depicted here in green. And today and going forward, we cannot use just one form of parallelism. We need at least 2, because we need to keep the local machines busy and multiple machines busy. So we're talking about using 2 very different libraries that have 2 very different ways of interacting with us. They have their own conventions, their own vocabulary. We have to somehow manage that on every single project we use. So this is literally like building a wall 1 grain of sand at a time. Really powerful, but we have to be careful. The second approach is completely opposite, taken by frameworks. And the way the frameworks work is that you look at the entire landscape and you pick a thin slice of the landscape and you take complete control over everything inside that landscape. And you turn around and say to the developer, if you want to solve anything in this problem, in this space, break down your problem in terms of map and reduce. Give me those 2 callbacks and I'll take care of everything else. That's what, those are what frameworks bring to the table. They tell us, the developers, give me callback for map, give me callback for reduce, and I will take care of everything else. This is great. provided I can break my problem into map and reduce. If I cannot use it. I have to use some other framework which has its own vocabulary, its own way of doing things. So this is like Model T in any color as long as it's black. If you like black, it's fine. If not, you can't use it. But there is merit to this approach, right? Because it does close the intent, the gap between intent and the API. It's just too restrictive. The vocabulary is not rich enough. It works in one situation and not other situations. Which brings me to the last environment, which is self-contained runtime environments. Now, in the interest of, there's an echo here. In the interest of disclosure, my company's product is the only one in this category. But put that aside. What do self-contained environments bring to the table? The ability to say, I want you to execute DAG right now. It will morph itself so that it can process DAG in parallel. When it's done, it becomes neutral. I turn around and say, now execute a list. It will morph itself so that it can process a list in parallel. And when it's done, it becomes neutral. So now all of a sudden, I have a single installation, a single binary that can be used to express multiple different forms of parallelism using the same vocabulary. Right? So that's what runtime environments bring to the table. Okay. Now, the cool thing about our definition of parallelism is that regardless of which approach you take, our definition of parallelism will work. At least I don't know of any exception. And the essence of our definition is just 6 words. Parallelism is all about the management of a collection of serial tasks. Begin and end of story. Any parallel capability must have 3 parts. A notion of a manager, not a scheduler, manager. Manager has to schedule and do other things. It must have a notion of a serial task, and it must have notions of communication primitives. The manager has to enable and disable communication primitives. Now that may seem really odd, but we will see ramifications of it. And of course it has to do scheduling, which I'm sure all of us are familiar with. Again, what it means for today's tutorial is we have 3 forms of parallelism, so therefore we have 3 ways by which to manage things, so therefore we will have 3 very different sets of policies. Serial tasks come in 2 flavors, coarse grain and fine grain. Everybody knows what this means, right? Coarse grain, fine grain? Anybody? Any issues here? You run GCC compiler 1,000 of those things on 100 machines, that's coarse grain. Because there is no need for the individual task to communicate until the very end. If you need to communicate before you conclude, that's fine grain. So this is what parallelism is. It defines what goes inside a GPU card, inside Intel's mic, x86 cores, and inside servers. So again, to summarize, what management policies focus on is how the serial tasks are managed, not what they may be doing. So in our examples, the examples are written with certain things in mind. You can certainly go home and change the notion of a serial task, and the rest of the examples will continue to work. This is the reason why it does. And this is nice, because I'm no longer pitching in the dark. There was a very nice report issued by the National Academy of Sciences late 2011. It's a report that explains the entire history, past, present, and future, and it acknowledges, this is a direct quote from them. But the mysterious thing is, they mention this, but there's no one section on it, there's not a page on it, there's not a chapter on it. They acknowledge it and then they won't build on it. No matter, we'll take credit from anywhere. Or not credit, but validation. Okay, so now we have defined what parallelism is. Let's go, this is the essence. Think of the big picture. Don't think in low-level details. Of course, there is no free lunch here. Right? All of us are able to drive a car without knowing anything about the gearbox or the transmission or the engine. That doesn't make us stupid. It allows us to do other things. So with parallelism, if I'm able to express parallelism at a higher level, let the equivalent of a mechanical engineer worry about the low-level details. Imagine the world where in the morning when you want to start the car, there's a spec that says you have to be a mechanical engineer before you can even start the car. We'd be lucky if we had like 50,000 drivers in the world. The reason we are able to drive a car is because it protects us from the dashboard, protects us from the low-level details. What we want is when we exploit parallelism, we want the equivalent of dashboards. Not everybody needs to work in the lower level details, and certainly not the domain experts. Okay, so here's an example. I'm trying to do my level best to give you examples of actual Python code. So here's a typical example of a serial module where I have a serial task. The one thing to note about this is not the content, but the fact that the serial task is a function of the arguments. If it's a function of the arguments, if I invoke it 100,000 times, they're going to work on 100,000 different things. So that's one very important thing to recognize. Right? Everything inside the body is a function of those arguments. If that is the case, we can invoke it multiple times with different arguments, at least in this case. Here's another serial algorithm. This is a slightly different one, and what I have here, you see this rank D. It's basically a rank order. It's given a unique ID. I can use it to create all kinds of temporary scratch pads and things like that. I can have a setup, a simple thing like that. I can have a situation where experiments are running that take a terabyte worth of data. But because of this number that has unique properties, I can have a footprint of only 20, 30 gigabytes. All the terabyte data is generated because all of it is cleaned up in real time. All because of that number. And there are several ways by which to generate it. But again, the principle is everything inside the body is a function of the arguments. So this is a serial piece of code. Here's an example of a parallel code. 3 things to note. I have a singleton parallel manager. It's interesting, it only accepts a single task. You would wonder why go through the trouble of creating a single, why not just evaluate it locally? There are advantages to that. But anyway, assume that this thing accepts a single task, so we create it, we push it. Over here, we execute the manager. This manager is not going to come back until the thing is accounted for. There is no more need to check websites or emails or anything like that. This is guaranteed to work, provided that semicolon is very powerful. Have you noticed when using debuggers and you have A equals 10 semicolon and you're at the beginning of the A equals 10 and you say next, where does the debugger stop? It never stops in the middle of A equals 10. It stops at the end of A equals 10. Why? Because that's the place where everything has stabilized, which allows me to then go in and say print a value of A. This semicolon over here says that the system has completely stabilized now, allowing me, the developer, to say, okay, if there is nothing stale here, go on to the next thing. No more hacks, no more websites, no more emails. And this is in the context of a serial task. What that semicolon represents is the parallel sequence point. A equals 10 semicolon, but in the context of a system. It guarantees that the entire system has stabilized now. Okay, fine, on to the next statement. Here's another example where I'm creating a list of tasks in the body here, here. I'm returning to the decorator, which then turns around and invokes the evaluator. Now if you notice, this body is different from the previous case, but this is pretty much the same, which is what we want. Clearly there's a difference between these two forms of parallelism. The list actually goes on and on. But that semicolon is very, very powerful. If we don't have a parallel sequence point, and we can discuss offline if people are curious. If we don't have a parallel sequence point, you know what happens? We have to compensate for it. How do we do that? We write scripts that say, is it done yet? Is it done yet? Is it done yet? And those scripts are tens of lines, hundreds of lines, thousands of lines. All that goes away and is replaced by a single character. Okay, now a parallel workflow. At the top level, it looks like where's the parallelism here? It's all serial. I'm importing modules and then I'm invoking them one after the other. But this is a parallel workflow because each one of these modules is actually executing parallelism under the hood. I don't care about those details at this level. This module is actually from production. It was created by a person who thought of this at the beginning of the hour. I'm just giving you the time frame. Within 5 minutes, this was authored from concept to implementation, 10 minutes to validate it on a laptop, 20 seconds to push it out into the cluster. By the end of the first half an hour, it's already processing hundreds of gigabytes. Why? Because I know what these modules are doing individually. I just want to create a flow now. And that semicolon is very powerful now because it says the system has settled. Okay, fine, go to the next thing. And he says the same thing. Okay, go to the next one. Okay, now the story I mentioned until now had to do with parallelism across servers, and Python played a central role in it. But it runs out of gas, Python does, inside a node when we have multiple devices. So I have a visual representation of multiple chips, GPU and Intel mic, all on a single server. Okay? Now the question is, how are we going to keep this busy? Yes? Yeah, I'm almost there. And how are we going to keep this busy? And just like before, we have a question. We have 4 modules we want to invoke, or 4 kernels, and we have to answer the question, how are we going to manage? Turns out Python doesn't have the syntax or the semantics to express that. I'm talking about management here. So here's an example of something written in Emerald. If you're interested, we can chat offline, and it's scheduled to come online middle of the year. It's tightly coupled with Python. So you get the best of both worlds, the world that we are all familiar with, and the ability to express incredible capabilities on these devices with very little effort. Okay, on to the next thing. A couple of big points in conclusion. Don't want to get lost in the low-level details. So the first, most interesting one is most embarrassingly easy form of parallelism. They actually perform a lot of redundant work. I always get a kick out of reading press releases that say we use 100,000 cores or 500,000 cores. It's like, okay, you brag about it once, but don't do it again and again, because it says that you haven't pushed the limits. There's a lot of redundant work being done. Analogy is, if you have 1,000 people working on something and they're not allowed to share any knowledge, there's going to be a lot of redundant work, right? There's going to be a lot of reinvention of the wheel. So it is with parallelism, only the scale is just massive. So the only fix here is to share knowledge. And if you share knowledge, Monte-Carlo simulations can be off by a factor of 500 just because we shared knowledge. The other one is HPC and analytics are memory bounded, which means they may be CPU bounded, they may be IO bounded, but they gobble up all the memory, which means that we have no choice but to use all forms of parallelism inside a node. We can't just have it serially executing things. Okay? And this whole business of prototypes versus runtime environments. Python allows us to prototype, but that prototype has to be executed by something. It's the Python interpreter. When it comes to parallelism, when we say we are prototyping, this is what we are doing. Agreed? We are constructing by correction. But the underlying parallel system has to be this, completely opposite. So if we were to share for you example, the guts of SPM Python is written in C++. If somebody were to perform a CAT scan of it and compare it to traditional C++ code base in NumPy, SciPy, any popular thing, you'll see the difference is night and day. It's unlike anything, at least in the open source world, because it demands that. It just has to work. And if it doesn't, it has to fail with known reasons. There cannot be a mysterious crash here. Enabling and disabling communication primitives. I said that we have to express parallelism using managers and not schedulers. I said manager has to do scheduling and a couple of other things. This is one of the things. So here's a situation where I have a communication primitive that's been used inside a module, and that module does such a wonderful thing, 3 different people using 3 different forms of parallelism are interested in using it. A fair request, right? What you're going to see is that the same module, same communication primitives, same machines are going to work in one context, are going to mysteriously result in a deadlock in another context, and in the other situation it will frequently deadlock. Now how can that be? How can the same code and the same machines behave so differently? Because of the nature of the parallelism, and they are very different here, and how they handle premature terminations. What that means is when we talk about parallelism, we can't just say, here's a communication library, go ahead and use it. Because our definition says there has to be a notion of a manager too. And the manager has to decide whether that communication primitive is safe or not. And if it isn't, it cannot be used, no matter how fast it is. 0MQ has a section to their credit where they explain in vague terms why certain situations are this. I suspect their reasons are different, but at least to their credit, they're upfront about it. It's because of this. Same thing with parallel data structures. Parallel data structures are nothing but communication primitives under the table. You can't have a global, all-purpose parallel data structure. It will not work. division by zero. In the serial context, when a division by zero is encountered, what happens? Process dies. In a parallel context, the same division by zero has to be interpreted in completely different ways depending on the nature of parallelism. So if you have a division by zero in the first context, it's going to say, no big deal, I'll produce a partial answer. In the second context, the same code could have a division by zero over here, and the manager has no choice but to shut everything down. It's the same code, same machines, but completely different behavior. And in the third case, it impacts the future. Not the present, not the past, but the future. Because the nature of parallelism demands it. Okay, so for the rest of the tutorial, 3 things to consider. As we are going through 3 forms of parallelism, answer these 3 questions. What is the management policy? Use your own words. Give an example of a compatible communication primitive that you can use no matter what. It will never hang. And lastly, give an example of a communication primitive that is toxic. If you get all 3 for all 3 of situations, you have gotten the essence of the approach. Okay? Oh, your class. Today's class. Yeah, list, MapReduce, and object space.
How does that sound? Can you all hear me? Okay, perfect. Okey-doke, so Minesh has introduced us to some of the theoretical underpinnings of thinking about parallel systems. We figured that was an interesting change from last year where I was entirely pragmatic looking at parallel systems. After this, I don't know when, but somewhere in one of the open sessions, we're going to schedule a parallel computing open session. The intention being that those of you that really want to get into the subject come along and we can talk about it and either share gained knowledge or solve problems between us because everyone is doing different things. So on that note, how many of you are interested in parallelism purely on one machine? So looking at multi-core but single machine. You put your hands up? Okay, about a third of you. And how many for multi-core, multi-machine, but up to say 5 machines, so a handful of machines? Okay, another couple of you. And how many for more than 5 machines? Many machines. Okay, that's kind of a third split each way. That's interesting. I would love to speak to you after this or in the bar or at the open space to learn more about your different needs, partly because I'm one of the organisers of what will be Europe's first Pi Data conference in London later this year in November. And one of the things I want to look at is the use of big parallel systems. So use cases will be very handy. So I am going to talk now a little bit more briefly about lessons learned working with parallel systems. So some pragmatic lessons learned. So the goal with parallel systems is always to build robust systems, accepting that there's going to be increased unreliability. It's one of the biggest things. How many of you have been dealing with parallel systems for over a year? Right, so at least a third of you have gone through the mill of figuring that your system was fairly well defined, the data was clean, the systems worked, and then at 4 in the morning things die, and then you have to start thinking about how you make systems robust for all the various ways that they can die. And once you're dealing with that, you have to think differently about reporting and debugging. Debugging a parallel system is very difficult. And it's not just CPU-bound tasks, we can talk about disk-bound tasks and I/O-bound tasks when we're dealing with this. And so at previous PyCon last year, EuroPython and EuroSciPy have covered different angles of parallel systems. Everything's online, the tutorial material, the videos, the code, all in GitHub. So if you're interested in things like profiling CPU-bound tasks, visualizations of the profiling, thinking about speeding up NumPy array accesses with num expression, dealing with IPython cluster to use IPython in a cluster environment, or offloading that to the cloud using, say, PyCloud, which sits on EC2, or going down to CUDA, you'll find that there's past material there, and I'm happy to talk about that, but I'm not covering almost all of this time. And so briefly about me, I'm a data scientist, whatever that means. I used to call myself an artificial intelligence researcher. The term is now data scientist, so I wear the data scientist hat. I've been working with Python for 9 years. I used to be head of technology for an AI research firm, and for the last 6 years I've been running my own research firm, and I do a lot of NLP work, and that tends to involve a lot of parallel systems. So we've taken the photo, which is great. Scalability issues. Whatever you specify when you're coming up with a specification for a system, you will specify it incorrectly. That is my simple experience of these things. Whatever requirements you're given by a client, by your boss, by your partner, the specification will change, and whatever thing you thought you had well defined, there will be elements of the spec that break. One of the worst things to do is to come up with a really light specification and decide to fill it in later, and then by the time you've got to production ready and you realize that the spec that you never really made, that was vaguely defined in all of your different heads, is really, really wrong. That was a situation 4 months ago when I joined the project, which was quite difficult to catch up from. So you have to specify things, but you accept that it will break. It's worth thinking about separability in your systems to make them easy to test and easy to understand and scale. So the worst way to write a chunk of code is to write a 30-page function. That's awfully hard to debug and maintain and extend. The same is true of parallel systems. You want many small units that are loosely coupled rather than one strongly coupled system. It makes it awfully easy to scale and bring in new developers and debug. And when we're talking about scalability, I guess you've heard of vertical and horizontal scaling. So vertical scaling is where you've got a 1 gigahertz chip, and then you want to go twice as fast, so you buy a 2 gigahertz chip and you go faster than a 3 gigahertz chip, and then you're stuck. Then you need to start going horizontal with multi-core or multi-machines, and then you expand out sideways. So we're going to look at some options around that with the multi-processing module on one machine, and then parallel Python and MapReduce to go across machines. And you have to assume that your cluster size will change in bigger production systems. Many parallel systems are written with known constraints. It will only ever be 5 machines because we're only processing 1 million messages per day, and that's the hard limit. And a year later, those limits change, and then the early design is broken. So my hard-won experience there just tells me to accept that your requirements change. How many of you use VirtualBox in your development environments, development situations? A couple of you on Vagrant? Okay, so VirtualBox is great for standardizing a development environment. It's especially great, I look at the number of Macs in the room, you typically don't deploy parallel systems to Macs in the cloud. You deploy them to cheap PCs running Linux in the cloud. And so you really want your deployment environment to match your development environment, or at least your test environment. And so a VirtualBox or Vagrant, a command line equivalent, is a great way to standardize your testing and your development environments. And you ought to be designing for multiple environments. You can design for just one environment, the design development environment, but really you want to have staging environments so you can think about upgrades and refactoring and testing and debugging, especially when it comes to re-architecting. I'll skip the notes about coding, I think. I've mentioned that lots of failures will occur. They bite you in the backside all the wrong times. There's a great long post, Notes on Distributed Systems for Young Bloods, where someone who's been doing this far longer than me lists all of the ways that he's been bitten in the backside. That's a really nice post. So if you just search on Notes for Distributed Systems for Young Bloods, or click on that link, there's a really, really good post behind that. I really recommend it. All of these slides will be online in the GitHub repo and posted onto my blog after this. So you can get that link. If we want to talk, if anyone's interested in talking about queuing approaches, I'm happy to go into this in the open session. But I think in the interest of time, and so we can do something pragmatic, I'll jump through some of this. Yeah, reporting's boring. Tool choices is kind of interesting. One thing I don't cover here, and I regret not putting it into these slides, is Gail Vedequar's JobLib. So I'm going to talk about multiprocessing, the built-in module, one of the batteries included modules. It's the one bit where we're going to do a bit of coding. You're going to write 7 lines of code. If we'd have used Gail's JobLib, it comes with some extra constraints, but we could do that with a decorator. And so having gone through the tutorial, it's worth looking up, if you're going to use multiprocessing, it's worth looking up JobLib, because with a decorator, you just auto-magically gain parallelism on your machine for a single machine. One thing that's quite dangerous with parallel systems is the not invented here syndrome kicks in. I'm completely guilty of ignoring celery and writing my own parallel distributed, fault-tolerant, scalable, wonderfully available, report-driven parallel system. I spent months working on one of those when I should have been making IP behind the project I was working on. It was my own project. I kind of lost months by doing not invented here and building my own rather than using celery. There are lots of interesting parallel systems out there, going all the way through to Storm, a big parallel real-time system for dealing with streaming data, large volumes of streaming data. Often they're badly documented, but it's worth the pain of getting through the lack of documentation because someone else has gone through all the pain before you, and they're bound to have hit all the hard problems and solved them, which you're going to hit later anyway. And one thing I'm always surprised about is the range of errors that can occur in any practical system. I was working off of the Bitly API a couple of months ago. The Bitly API is quite nice. It's got nice Python bindings. Everything looks sensible. Every now and again, the Bitly server throws a 500 internal error, but it's kind of once a day it throws that error. So you have to catch that. And then after a while, you start to get timeout errors. Every now and again, you'll get local DNS problems, and then you'll get a Python connection error where the connection gets dropped. These things are very intermittent. If you don't start baking the idea of a good, solid test framework around your parallel system, and then you start to scale out, all of these very infrequent errors will occur more frequently, and it'll make your code very difficult to support. So you have to assume that these many errors will occur. And if you're not familiar with all those tools down the bottom, then if you're doing any debugging of parallel systems, those tools are very, very interesting. HTOP is a bit like TOP, but it gives you a multi-CPU breakdown of what's happening in your machine. DSNF, list of open files, interface top, so a top that tells you what's happening on your network interfaces, and netstat. And Glance is a Python tool that wraps up a number of these and then lets you report from multiple machines. If you're dealing with 30 machines and you're having to SSH in and try and diagnose them one at a time, or understand why at 4 a.m. things went weird, these tools make your life a damn sight easier. And things like Supervisor D and Upstart for having a machine restart and your processes coming up. There are cleverer solutions. The best I've got from friends working in startups in London is that Upstart, one of the Ubuntu basics, is just the system that generally people seem to use, maybe with Supervisor D or Circus, and then Fabric and Puppet for deployment. So Salt looks lovely, only Puppet is the well-established package deployment system. And although it's got a weird domain-specific language and it's written in Ruby and so it may not be familiar to us, it's a damn sight more bulletproof from what I understand than Salt. And so I would use Puppet backed up by Vagrant to have a deployed environment and then have a matched version in the cloud. I'd love to see Salt mature. Circus looks great. It's supported by Mozilla, but I've had some weird errors with that. Supervisor D is older and far more boring and has got a weird ini file structure. Just seems to work. And after a while, you just want these things to work. When it goes wrong at 4 in the morning, and you've got 10 machines with overflowing queues, and then you've run out of debug space, and you've run out of logging space, and you can't see what's going on, you just wish you'd chosen the thing that was 10 years old and just worked. So now we're going to do something a bit pragmatic in the run-up to the first break. So we're going to review list of tasks. So the goal in this section, you're going to use your virtual boxes. I'll show you how to start the virtual box, but then I'll use my host machine. I think it just works better with the projector setup. We're going to deal with the simplest problem of dealing with a CPU-bound task running off of one machine and then maybe multiple machines. The fact that you're all using virtual boxes makes it harder to get machines to cooperate, but I found a way through last week, so I think we can show multi-machine communication going on as well, which is kind of the point of this tutorial. So we're going to tackle a CPU-bound problem. It's the Mandelbrot set. For anyone who has been in my previous tutorials, really sorry we're doing the same Mandelbrot set example again for this section with a few twists. And so the goal is to use all the cores on this machine. This is an 8-core machine, 4 physical cores with hyper-threading, giving it another 4 virtual cores. So it pretends to have 8 cores. So we're going to use multiprocessing that's built in. We're also going to look at Parallel Python, which is a third-party module which does automatic pickling of code and data for distribution to other Parallel Python machines. It's kind of a venerable solution. It's been around for a while. It seems to be well understood. We're also going to look at HotQ, which is a queuing system using Redis as a task storage system with multiple Python instances talking via Redis, which can happen on one machine or on multi-machines, and enables you to deal with task distribution to non-Python systems, because you've got Redis as a data store. And we're going to use some matplotlib for some visualizations. So we are first of all going to generate the Mandelbrot set. And I've made a pretty surface plot, so it comes out in a lovely 3D output. It turns out generating a 250,000 plot 3D surface plot takes far longer to generate the plot than it does to generate the data behind it. So we're going to generate a really simple one at the command line. But you're very welcome to run that if you want with the full space on your own machine. It will take a few minutes to generate the plot. So this is what we're going to run. So first of all, I would like you to start your virtual boxes. So for those of you that have your working virtual boxes, you just go into the VirtualBox Manager, click on the PyCon 2013 image that you've all installed. You installed it using the machine add, and then just, it should say, I think it's run or start up here. So click on run or start, and then we go into the VirtualBox, and then will be in here. If you get the screensaver, then the password is PyCon. Username PyCon, password PyCon. For those of you that don't have the VirtualBox running, if you want to get it running during the break, then I can stick around for that and we can get it running during the break. And some of you have asked how you get it off. At the end of the session, we can get all the VirtualBoxes off of your machines again as well. So inside the VirtualBox, can everyone see this clearly enough? Is this big enough? Okay, shout if it's not big enough. We start at the home directory in PyCon. You're going to want to go into the PyCon 2013 directory. So CD into PyCon 2013. You can use tab completion. And then we have some subdirectories. This contains all of the running code. We're going to go into section 1, list of tasks. In fact, I'm going to live dangerously and try and run it from all in the VirtualBox. And we'll see what happens. That might make more sense for you guys. That one. How can I make the font bigger in here? Anyone? Okay, that'll do. So we want to go into one Mandelbrot serial. So we're now in PyCon 2013 Applied Parallel Computing. One list of tasks, one Mandelbrot serial. And then use gedit to open up serial Python, and you probably want to put an ampersand at the end, otherwise it locks the terminal. And fonts and colors, how do I know? Oh, that'll do. Okay, so this this Python module will generate the Mandelbrot set. We'll look at the code in just a moment. I just want to run it first of all so we can see it all running. So we're going to type in Python serial python.py --plot3d. So we'll type this on screen and size 100. So Python serial python. And then what did I say? --plot 3d and dash size 100. Let me just, yeah. Okay, so this will generate a small plot deliberately so that we can get the 3D plotting working. and then we get a low resolution. There is a reason why we chose the surface plot rather than just the 2D plot. First of all, has everyone got it displaying on their screen? Yep, it's come up, okay. Some of the graphics in a later section don't show up on screen and we have to use an image viewer. I don't know why that is in the VirtualBox, but as far as I know, all the pill visualizations work. Show the command. So the command is this one here, Python serial.py -- plot3d -- size 100. So if I drag this out of the way, the reason for doing the 3D surface plot is because we want to think about the fact that with the Mandelbrot set, there are a number of points that are cheap to calculate, so the coordinates down in this corner, down at the lowest height. We count the number of iterations per complex coordinate to generate the Mandelbrot set. Whenever we exit the loop early, we count the number of iterations. It could be 0, 1, 2, 3, whatever, limited to 1,000 in this case, I think. And then I'm representing height as the amount of work every coordinate takes to calculate. So the simple notion being that if we're down here, it takes no time to calculate. If we're calculating in this area here, we have to keep climbing up to the top of these spikes, and it takes a long time to climb up. So we just want to have this notion in our head that some of the coordinates are complex to calculate and take a long time, and some of them are cheap to calculate. And depending on how we divide this space up to share the work out to multiple machines, some sections of calculation will be cheap to calculate. Say this entire strip here will be very cheap, and this entire strip here will be very expensive and will take a long time. So we have to think about how we divide our work up. So if you wanted to generate the big plot, you could just take out the -- size 100 and it will default to size 1000. It'll calculate in about 25 seconds and then spend several minutes drawing itself. So we're not going to use plot3d. I want you to run it again, Python serial Python, but without the 3D or the size 100. So just Python serial Python. So this is going to calculate the harder version of the problem. So just Python serial python.py, hit return. This is going to calculate the more fine-grained version, but only plot it in 2D, so we get a quicker solution, but something that takes a little while to calculate, such that it's worth parallelizing it in the first place. So now it goes quick. You saw that it went quite slow in the middle. That's because when it gets to the middle of the calculation range, we're up near where that mouse pointer is, looking at that more complex section of the Mandelbrot space. And here you can see that white equates to very high, and grey is of indeterminate height, or intermediate height, sorry, and then black is down in the very cheap to calculate space. So let's very quickly review the code behind this. Ignore the assertion error. The assertion error is there to check that everything's working on a 64-bit system. The VirtualBox is 32-bit, which should work on more machines. I didn't change the assert errors, so we can ignore that. So in gedit, the entire code, this is just all the code. Calculate Z does the real work. This here is a for loop which calculates for every complex coordinate what the height of each of the complex coordinates pillars will be. And then it breaks out telling us how many iterations were counted. So this is the serial portion of work that Minesh alluded to. We have a part that can be parallelized, and we're parallelizing many serial portions of work. So that's the serial portion. And down here, we're building up a list of complex coordinates that need to be calculated. And so in here we're generating, you can see X and Y. This is looking at the complex space I and J, but mapped to X and Y for easy plotting. So we're generating on the complex version of the problem, the one that ran quite slowly, 250,000 data points. So 250,000 points that need to be calculated, up to 1,000 iterations per point. And then all we do, and you're going to fill in some code here, so I just want to make you familiar with the code. We generate this list Q of 250,000 points, and then we time how long it takes to go through and calculate Z, calculating on those 1,000 points. We calculate how long it takes. We use PIL to show the output, the Python imaging library, and then in the terminal, we just note that it takes, in this case, 20 seconds to calculate the 250,000 points. And so the goal is, how do we go faster? So, 11 seconds on my laptop instead. It's a bit slower inside the VirtualBox. Something always to remember when dealing with parallel systems is that Amdahl's law kicks in. There are some sections that are parallelizable, some sections that are not parallelizable. If this is your problem and you've got a chunk that's not parallelizable and a chunk that is parallelizable, and you make it 10 times faster, and you've still got this serial chunk of work that just takes a fixed amount of time, it doesn't matter if you go 10 times faster or 100 times faster, it's still going to take this long to get all of the work done. I once worked on a system using a CUDA card a couple of years ago to work on a physics problem. I made it 100 times faster. I'm super excited by the result. It made the physics simulation much faster for the boss. Turns out the system that calculated the data that was passed into my CUDA routine still took 30 seconds, and then my fraction of a second result was wiped out because it still took far too long. It's horrible when you make that kind of mistake. So think about what serial constraints might exist, and also think about how much memory might exist. So if you're dealing with parallel systems which are going to distribute data across a network, you need to think about the data and the things that might affect the transmission speed. And so one thing to consider is how much memory we're using. So how much memory are we using in this problem? And so I have a partial answer for you, and I'm hoping someone will be able to discuss this with me. Oh, let's just do it with Python. So import sys.get size of, and if we ask it to make a complex number, on a 32-bit system, we know that one complex number costs 24 bytes. So 24 bytes times 250,000 comes in at 6 megabytes. We're also going to have a list, and a list will contain 250,000 elements, and that costs, I think, 2 or 3 meg. So we end up on a 32-bit system costing about 8 meg for this structure. And so this is the lower bound that we would expect. This is the memory that I know I can account for. But if we go back to the presentation, on a 64-bit system, it costs 32 bytes. I know on a 64-bit system, I can account for 12 megabytes worth of data between the list and the complex numbers, and yet using Fabian's memory profiler, which monitors externally how big a process grows, I know that the process grows by 25 megabytes. So there's 13 or so megabytes of data that I can't account for that's happening in the Python, somewhere in the Python interpreter. And this is something that I'm hoping to explore with some other people to figure out what's going on. I've actually got a small GitHub project where you can run the memory profiler bug, and it makes exactly the same data structure. We can profile it and see where the data goes, because I really want to understand where this extra data goes. If any of you are interested in this and we can discuss this in the open space, that would be cool. So let's switch over to using multiprocessing now. I just wanted to put an aside in thinking about the memory, because if you're dealing with memory and a network and throwing a lot of data around, you need to have an idea of how much data is being sent around the network. But let's just look at making this thing run in parallel now. So we're going to use the multiprocessing module. It's built in. By siloing sections of our work, we can easily test them. We've mentioned that before. Multiprocessing's one limitation is it only works on a single machine, so it can't parallelize to multi-machines. But it is built in, so it comes for free. So we're going to split the work into chunks. So rather than one long list of 250,000 elements, we're going to start with one long list and then split it into smaller chunks and then send those out to different CPUs. And we're going to use the map async function. And then we're going to get the partial results back, join them back in order, and then have a result list. So this is the bit of code that we need to put together. So we're going to open up the second example, not the serial Python example, but the multiproc example. There's a section that says students write code here, and we're going to expand this bit of code and then finish off the last point there. We're going to make a multiprocessing pool. The pool by default has as many units or as many workers as there are CPUs on your machine. So on the virtual boxes you've got, I think there are 2 cores defined. On mine, I think I put it up to 4 cores. So for me, the pool should have 4 items in there taking work. And then we'll use map async, giving it a function, that calculate Z function, and arguments, giving it the partial items of data that need to be calculated. And then we'll ask po.get, which is a blocking function, to submit all the work out, and then wait for the answers to come back. And then we're going to join the results together by hand. So I'd like you to type along with me. So in here, no, come on, in here, then we want, so the directory to Mandelbrot multiprocessing, and then actually I'm going to use gvim, which I've got installed. You're going to have to use gedit. I'm just going to make sure I can type fast enough that I don't hold you guys up. Let me just. So down here we should have a section that says students solve this section. So, oops. So does everyone have students solve? Does everyone have students solve this section? We're going to type in some lines of code here. So I'm going to have you typing after me, please. So I would refer back to the slides, but swapping back and forth is going to be silly. So we're going to make the multiprocessing pool first of all. So P equals multiprocessing.pool. So we make a pool of workers. Oh, we need start time. That's annoying. Say again? So you have to type in 4 spaces, I think, in gedit. Is that right? Yeah, sorry. So in the instructions that it turns out didn't get sent out, it said gedit is installed. You probably don't want this editor. You probably want to set up your own environment so you can type along at your own comfort. No one received the instructions, so you've got gedit. But that's why I'm using gvim that's installed in mine, so at least I'm not holding you guys up whilst I put the code in. So start time, I ended up cutting that line out by mistake. So we need start time equals datetime.datetime.now, just to match this end time down here. And then we need to fill in a bit of work. So we are going to ask the pool to asynchronously map the work using the calculate z function and chunks. Now chunks is referring to these lines up here, where all we've done is said, how many chunks of work do we want? Well, we're going to start with 1 chunk of work, and then we're going to divide our list of a quarter of a million elements into 1 chunk, so we're not going to change it. But if we want 2 chunks, we divide that list into half. We want 4 chunks, we quarter it. Because we might have an uneven number of chunks, so we want to divide a quarter of a million by 3, then we have to do a little bit of messing around with the numbers to make sure we get roughly even sub-chunks. But that's a boring bit of code, so I'm not going to make you type that in. So we're just going to use these chunks of work that we have predefined and pass them to the map function. And then we're going to ask for a set of results when they come in. So this is a blocking function. So po.get, we're going to get the pool object, that's the result of the p.mapasync. We're going to ask it to get the results. If the 0th result comes back first, it's great, we consume it. The first result comes back and we consume it. If the first 2 final result came back and the 0th hadn't come back, then it just blocks until the 0th comes in, then it all comes through in order. So the ordering is handled for us. That's very nice here. In the parallel Python example, that's not the case. And then we get a list of lists of results. In the original serial version, we just had 1 list with all of the results inside it. So we need to flatten the list of results into a single list. So we're just going to do a really, really simple flan for partial result in results, output plus equals res. So we're just going to take all of the list of results and turn them into a list of single numbers. And then that should be the end of the code. No, that wasn't indenting for me. Have I done a typo? I think that looks right. So I'm just going to run this and make sure it does actually work without... I don't want to force you to type in something where I've got an error. Oh no, okay, that's perfect. That'll go away. Okay, so how many of you are still typing this in? Okay, I'll leave it up. Oh, have you got a question? Oh, so have you got, is Vim installed? Yeah. Oh, perfect, okay, so. So, I'm just going to type as if anyone else might have to, but that's a good tip. Maybe I did set up GVim in this version. We had several virtual boxes at play. I didn't realize which one I distributed. Is anyone still typing this in? Okay, one person. Okay, I'm just going to run this in the background now. Are you good? Yep. In fact, what I'm going to do up here is first change. So I put number of chunks as one. So one chunk of work, so we could only use one core. So I'm going to change that to 4 chunks of work. So we divide the work up into 4 units. And then we're going to send out 4 jobs asynchronously. On a 2-core machine, that means that terminal's dead. So I'm going to run multiproc.py. And you're going to see an interesting thing happening with the work. You're going to see the numbers appearing out of order. That's where the 4 different processes, their sub-processes, are passing back standard out, and it's being printed out of order. And so we're seeing the 4 bits of work come through, and then we get the Mandelbrot set. It feels faster. It took 10 seconds this time, which is faster than the 20 seconds that it took before. So we are using more cores, and if I run system monitor and run this again, then what we should see in here is that all of the cores bounce up and some work happens. But we're going to see something interesting in there, and I'm going to ask a question about it in just a moment. So we see the CPU usage climbing up, and then we see 2 of the cores finishing earlier, 2 of the cores working for a while, and then everything dropping off. Actually, it's a simple question, so I'll just tell you what's going on. We've divided the work into 4 chunks. 2 of the chunks are near the center of the plot, so that's the harder work. 2 of the cores work for longer. So the easy way to get past this is to divide our work up into more chunks. So if we go back and just turn that 4 into 32, then this whole thing should run a bit faster again. And so now, even if one of the tasks that was working on the edge of the problem finishes quickly, then there's still plenty more work elsewhere in the problem space, which you can go and pull out. And so this time, where did we get down to? Down to 7 seconds this time. And I know that we can't go much faster than this with this particular system. So here we're using efficiently the 4 virtual cores inside this virtual box and your 2 virtual cores in yours. Does anyone have any questions at this point? The script. Which lines do you want? Number chunks? Further down? Question? System profiler is this icon down here with the heartbeat-like squiggle on it. And you had a second question? Yes. What's the best setting on these? So in this virtual box, it's about 7 seconds. I can, on my native machine, I can get 64 work chunks and it goes a bit faster, but that's about as fast as it goes with native Python before you get down to using NumPy and other solutions. And that's part of what I've taught before, but I'm not going to cover that this time. So that's multiprocessing on one machine. It's the VirtualBox itself. If you don't have the VirtualBox extensions, the guest-in extensions installed, then things can run slower in the VirtualBox, but also there's quite an overhead in the VirtualBox itself. So we do see an improvement, but it's not a doubling of speed from 1 chunk to 2 chunks, and you certainly don't end up with a massive improvement. On my native machine, I get a much better improvement, and it's just the overhead of the VirtualBox. It's great for having a separate dev environment, but it's not great for CPU-bound tasks. But it's great for distributing an image for everyone to be up to speed for teaching against. Okay, so I'm going to jump out of this, I want to make sure we try and keep to time with the upcoming break. So I'm going to go back a directory and into parallel Python. In fact, I'm going to cheat and call up the solution. Yep. Yes, so yours all have two, because I wasn't sure if, I thought everyone would have at least 2 cores and the VirtualBox would run without an error. But if I told you to have 4 and you only had 2 cores, I didn't know what errors might happen, so I was conservative. And again, that was mentioned in the setup instructions that never got distributed. So here we're going to look at parallel Python. A quick look at this module. So parallel Python, we end up doing almost the same work as the multiprocessing module. So I like this module because we can use the built-in multiprocessing module to get single machine speedups. And you're not going to type anything here. I save you from typing here. It's a tiny bit different in how we set the code up. Annoyingly, it's not quite the same interface between parallel Python and multiprocessing, but it's pretty simple. So we create a server, pp.server at the top there. So we ask it to make a server that can handle jobs. And then I'm printing out how many CPUs do you see in this machine. And then I ask for all of the chunks of work that we've got to submit each chunk of work to the server. I'm telling it to pass in the calculate z function, so we almost did that before, and then passing in chunks of work as a tuple and ignore the other arguments. And then we get back an asynchronous job object. So this tells us the job's in flight or it's finished. And then we append the number of these job partial results onto this list. And then we, down here, we put brackets around the job function. That makes it block until the result comes back in. So it's the same as the blocking get that we had for the multiprocessing module, just a slightly different output. And then we do plus equals on the output result to append it, to flatten it into the output list. And then we get back exactly the same result as we had for multiprocessing. The difference is that this will work on one machine or on many machines. Now, what I'm going to try and do is demonstrate an aspect of multi-machine work here, which is a bit tricky with all of you having virtual boxes, because your virtual boxes can see the internet, but it's a bit like you being at home behind a cable modem router. I, from outside here, can't see into your virtual boxes because they're not configured that way. But I believe that I can set my machine up to be a server which can accept work, and some of you can post work to me. And I'm not going to do that in the virtual box because that would be, just not going to work. Where's my command line? Right, I need a willing volunteer who is quick on the keyboard. Right, you sir. Please open up are you in the solutions directory? So in the solutions directory, you've got parallel pi many machines.py. If you open that up and scroll down, you'll find this section. Can you read that back there? Can you read the screen? Just the line that has the IP address on it. pp servers equals. Okay. So pp servers equals, and then there's an IP address, and we've got to fix that IP address. So find the line with the IP address. Find the line with pp servers space equals and a tuple. And then let's find out what my parent machine is. Have you found that line? No. Is there another willing volunteer in the room? Another willing volunteer. Find the pp servers line. Have you got it? So put in the IP address. So it's a string IP address. 10.35.3.223. 10.35.3.223. So your machine is going to post out from its virtual box onto the network and try and talk to my machine. Okay? And I have to remember how I do this. So I'm not going to run this bit of code. Oh my goodness. And I'm just going to read this off my local machine here. is my command, magic command, pp7.py da. So pp server, that's the parallel Python server. I'm going to run ppserver.py. -d gives me debug messages, and -a advertise. So my machine is advertising itself for work. So it'll open up an external port. So I now say, I'm ready to do work. Who wants to give me some work? You, sir, want to give me some work. So if you just run parallel Pi many machines, then we're going, well, we should see some work coming through here if we got that right. So are you running that from your machine? Well, I hope it works. Is anyone else trying it? You're trying it as well. Well, this is the point where magically, because the IP address is, the port is open, because PP server is running, and it's saying it's ready to receive work, then these machines post in. And this was validated. It was working. I'm guessing this is a network thing. Yeah, networking at PyCon, yeah. We're all running on a Wi-Fi network, so it's on the same subnet. Well, okay, maybe in the open spaces we can try this in a more controlled environment. What should happen is you post your work to me. Many machines can post their individual jobs to me, and I end up being just a slave sitting here working on the 8 cores, passing results back. And if we're running without virtual boxes, then you could end up with one of you submitting jobs to many servers like me, and then you end up with a really, really quick result, fraction of a second to get the results back. Really sorry that result didn't come back. Okay, and I'm just going to show you, because we're now just about at break time, I'm just going to show you the code for a quick code review of another solution. Maybe I'll do that back in here. So using a hot queue around Redis. So I'm guessing everyone here knows of Redis. Where do I set my work up? So Redis is an in-memory data store. It's great for caching data for websites. It's great for passing messages around. When you shut the Redis server down, it serializes its state down onto the disk. And so you can have PHP, JavaScript, Python, Perl, everything talking to a Redis server. You can shard the Redis server across many machines. So it's a great storage unit. It's a great queuing unit as well. So a cheap way to have a many machine system posting jobs out, and then maybe that machine goes away, and then other machines consume the work and post their results back. We can use Redis for this. And so there's a really simple solution out there called a hot queue. Originally a Ruby project, I believe, and then there's a Python version. It's just wrapping up a list in Redis with some simple list-like primitives. So we can ask it, for example, how long is the list? So down here, we have 2 hot queues, a hot queue in and a hot queue out. So on one of them, we put work that we want somebody else to do, and then the other machine consumes that work, and then it puts work back onto the answers queue, and then I, the server, can consume it. And you'll see it's the same formalism here. We split the work up into chunks. In this case, we have to do the sorting ourselves. So we put a chunk ID, that's the numeric ID 0, 1, 2, 3, for which piece of work we've got, onto the worker queue. And then we wait until the chunks of work have finished processing, assuming that some other machine is doing the processing for us. And then we reassemble the work, and then we get a final result. So I'm just going to run this here locally. I'm not going to try running it over the network, seeing as the last example didn't work. So I'm going to run hotqueue server. I'm trying to make sure you guys see this. Oh, where was that? Oh, yeah. So I'm going to run hotqueue server in this terminal. And so we're submitting a number of jobs into Redis. And Redis is configured on this machine to have an open port so that external machines could look in. And then in another terminal, I'm going to run hotqueue without the -- server flag. So this is going to be a consumer, and he starts to consume some work. And then I can do the same thing again and make another consumer, and he starts to consume some work. And then in here, the server side, it sees that certain computed chunks are coming back onto the queue. And then it won't take very long before all of the chunks of work are done. And then we get the completed result back. And that 30 seconds included the fact that we didn't have any workers running when we put the first jobs out. And so with this solution here, I've had this running over a network of 6 machines, but we're not going to try that example here. Am I? Yes, so all the partial results that are calculated, the lists of results are posted back onto the other queue with their ID. So whether it was the 0th result, it's prepended with a 0. So we can then take these partial results, which come in any order, sort them into the correct order, and then join them together. So this is a really simple queuing system. The downside of the hot queue approach, the upside is that it's a couple of lines of code and you can distribute to many machines in different languages, and it's all under your own control. If you're familiar with using Redis, you can use the Redis CLI monitor to introspect all the data that's flowing around the network. You can monitor it totally under your control. The downside is there's no communication primitives behind all of this, so we haven't got any control primitives. If a consumer machine consumes some work and then has an exception and dies, we don't post back the fact that that work will never be completed and someone else should do it. And that's where perhaps 0MQ or Celery comes in, because there you have higher level primitives dealing with work retries. But I've been using this, or this has been used in production systems where I've been involved. So even though it's quite simple, if you don't mind losing a bit of data every now and again, so you're dealing with large volumes of data continuously, then it's a really, really nice lightweight solution which parallelizes very nicely. So let's just come to the end of this section. Where's my... So we did that, we've done all of that. Oh, there we go, and it's the end of that section. Perfect. So we're going to take a 15-minute break. Anyone who wants to get set up with VirtualBox, stick around and we'll see if we get that set up. And then we'll work through the MapReduce examples, which will only run off of one machine in this example, and then we'll switch to Minesh's final examples. So if you want to work on the VirtualBox and you haven't got it, stick around. If not, 15 minutes back in here, please, and then we'll carry on. Thank you very much. So, can I ask, how many of you have worked with MapReduce in the past? Hands up. So, okay, still a bunch of you, not so many. And how many of you intend to work with MapReduce, or at least want to understand it, see whether you should use it? Okay, that's about 2/3. Okay. So we're going to look at a MapReduce system. We're not going to look at the standard MapReduce system, which is Hadoop, which everyone knows of and may have used. We're going to look at Disco, which is a more Python-centric solution. So we're going to use Disco from the Disco project. Disco stands for Distributed Computation. It's not about dancing and fancy lights. We're going to do a simple word counting example, and then we're going to do some filtering, and depending on how we do with time, maybe we'll look at a social network example around this as well. And we're going to have a brief discussion about practical configuration issues. The Disco project is a relatively young project. It's a couple of years old, maybe a bit more than that. It came out of Nokia. It's written in Erlang with a Python layer on top, so it's written in Erlang by people who understand Erlang, so it's a bulletproof system with a nice friendly layer on top, but it's written by people who are really in this domain. So there are tutorials on the website, but there are gaps in the tutorials that a beginner might fall over. And so we'll have a time, well, part of the reason for this walkthrough is I want to show you just how to get up and running practically. It took me a bit longer than I expected to get working with the Disco project. And so in the VirtualBox, we've got Disco pre-installed. It has some setup requirements, and I wanted to make that easy. Matplotlib, and then we're going to use a word cloud visualizer by a chap called Andreas. That needs scikit-learn and Cython and PIL. That's already installed. And NetworkX if we get to the social graph visualization. One of the interesting things behind Disco is it uses its own Disco distributed file system, so a robust, redundant file system. In a production environment, typically it will have three-way redundancy, so if one machine dies or two machines die, you've still got a third machine containing one section of your data which can be replicated around the spare machines. So it has a built-in robust file system. It also has a web management view, so you get to see what's happening. We'll look at that in a moment. And baked into the design of Disco is the assumption that your nodes will fail. When you've got 100 machines running, you know that some of them will die, a disk will die, a power supply will go, a network switch will die. So this is just baked in from the bottom up, which makes it nice and robust. Noting back to Minesh's points at the beginning about different communication primitives, in Disco there's no communication between nodes to share state about the state of computation. You could build something on top, but that's not built into the design of this at all. So the idea is you have a list of tasks that need to be solved, and then you solve them in a distributed fault-tolerant way, far more fault-tolerantly than we were dealing with in the earlier examples, and you don't share any state. But maybe you rebuild a task list when you've learned something about your problem space and resubmit a new set of jobs. You have a chaining option as well, so you can chain sections of map reduce to map reduce to map reduce, so you can chain larger jobs together. It's great for processing big data sets. One of the big uses of map reduce, it's become the system that is parallel big data solving solution for the world. Really one of the good uses of MapReduce in general is chunking through large data sets where you want to parallelize the number of disk reads and I/O channels you have in operation and the number of CPUs doing something that's typically fairly lightweight. So normally the CPUs aren't maxed out, but you end up maxing out network bandwidth and local machine bandwidth as you shuffle large data files around before you get a small result being sent back to a central machine. And we'll see that here. Whenever I come across MapReduce systems, or certainly in the past, I come across lovely diagrams. I believe I understand it. A day later, I think I still understand it. And a day after that, I think about the diagram and realize I've forgotten it. So what we're going to do today is simulate a hand-powered MapReduce cluster. And I've allocated my 4 virtual human machines over here who are going to do this. And so I'll show you I might show you the worksheet. One of you hold up your jobs, if you would. So we have jobs like this. These look just like the tweets that we're going to be processing shortly. So we have short messages. So we have single sentences with a couple of words. The goal in this task is to count the frequency of all of the words under the classic MapReduce system. So we're going to do a map, we're going to do a partition and shuffle, and then we're going to reduce the result back so that I end up as the master node with the final count of the words. And so we're going to do this by these kind people here. So take one of your work chunks. So you have a couple of words on there. Your first task is to tear the strip into individual words. And we'll be doing exactly this bit of code in a couple of minutes. So we're going to be splitting up our input lines into word chunks, which we're then going to do something with. So you've torn up your chunks, and do it for each of your chunks of work. So there are 1 or 2 sentences each. So we tear them up, and we have 3 to 6. What's going on there? And we have 3 to 6 words that need to be counted. Who has the word had in their work pile? Did I distribute the work really, really badly, so had went to one person? Well, there are a number of words that can be distributed around the cluster. Had, a, cat. Well, there'll be a set of words which are split around. Now we're going to go through the partition and shuffle step. Partitioning is the act of figuring out which machine is going to be counting up the same type of word, and then shuffling is shuffling the work across the network to the machine that will do the partition. So we need a partition function that tells us for any arbitrary data, in this case words, which machine will have those words to count up. So if we had a more conventional example, the would be the most frequent word that we would pass around for counting. Everyone would have some numbers of the in their word pile. We would need to figure out which machine the would go to so that that machine can count up the frequency of the. So whoever's got had, you've got had, it might be that you aren't the machine who will count had. The way we're going to do it, the partition function we're going to use is the number of characters in the word mod the number of machines in the network. So machines in the network, hold your hands up. So we have 4 machines in the network. So 4 mod 4 is 0. So you are the 0th machine, sir. You are machine 1, machine 2, and machine 3. Okay, so linear ordering. So if we have a 1-character word, like the word A, then 1 mod 4 is 1, and that goes to machine number 1, so that's you. If we have a 5-character word, 5 mod 4 is 1, and that goes to machine number 1. So, what's your first word? Pick up a word. Ben. Ben is a 3-character word. 3 mod 4 is 3. You're machine 3, so you keep that, okay? So Ben keeps that one, okay? Perfect. Ed. So Ed is 2-character. 2 mod 4 is 2, which goes to machine 2. So then partake of the shuffle function and shuffle your work across the network. Okay, gentlemen, I now need you to calculate mods in your head and shuffle the work around your small network. So 1 goes to 1, 2 characters goes to machine 2, 3 characters goes to machine 3, 4 characters goes to machine 0, 5 goes to machine 1, 6 goes to machine 2, 7 goes to machine 3, 8 goes to machine 0. So stake, 5-character. Stake 5, mod 4 is 1. You're 3. We've got a shuffle error already. Shuffle over to 1. So clearly the short characters are really easy to calculate, and when you've got more than 4, you have to think about it. So now we're seeing network contention take place, where the network bus is being contended by data being passed back and forth. Machines are communicating with each other, figuring out who can take work and pass it around. So here we're simulating with millions of messages the slowdown that will occur when there's too much network data being passed around, and that's a classic problem in MapReduce. So it's the work shuffled around now. So you should have words of 0 character, there aren't any, words of 4 characters, and words of 8 character. You're good? Words of 1 and 5 character, 2 and 6 character, and 10, and 3 and 7. Okay, just 3, perfect. And so now we need to reduce the counts. So the simple way of doing it is just to bundle all the words together, so that you've bundled your words together. So how many HADs do we have? So we have 2 HADs, at which point that work comes back to me. I'm the master node, and I know that we have 2 HADs. So we have 2 HADs, hooray! And how many, what's that large word there? Consumed.
1.
We have 1, so we have 1 consumed. So that comes back. And this way we reduce all of the partial results on the different machines back to the master node, such that the master node has a final count. Now there was an intermediate step, so that's the end of that example, thank you very much. There was an intermediate step that we could have done. The intermediate step is when we have lots of piles of the same word. So if we have the is the most frequently occurring word in the English language, typically in text. So if we ended up with hundreds of the, you could pass the individually hundreds of times across the network to the right machine, or each machine could bundle together their local copies of the, come up with a partial count, so I've got 50 these, and pass 1 partial result across the network. And so that's one of the optimizations we'll look at. But there you get the basic idea of what happens with MapReduce. So let's run MapReduce. So you're in your virtual boxes, I hope, and this will just run from the command line. I've put bin/disco, ignore the bin, that's an older version. So you're going to type disco space no daemon, D-A-E-M-O-N. So, and I'm doing this on my host machine. So disco no D-A-E-M-O-N. And then you should get some output just like that. So yes, it was disco no daemon. So up here, disco space no daemon. Does everyone get that output? Does anyone not get the output having tried it? Okay, I'll take that as a good sign. So here we have some Erlang error logging coming through. If you use disco, you'll discover that the Erlang messages can be fairly terse, not terribly clear on explaining when there are problems. Merely there is a problem, and it's up to you to figure out what this might mean. So here we have this running. We can see that starting node disco 8989 slave, so that's the name of the slave on this machine, on Ian latitude E6420, that's the name of this machine. And so we get some nice logging. And when we run multiple machines, they all start checking in, and we get an idea of the size of the network. Now we're going to go to the web browser. You want to navigate in your browser to localhost 8989. So localhost 8989. And now we should have a Disco status page. And although it's distributed computation, they have taken the Disco glitter balls and used it as their logo. So there are two sides to this page. We have status and configuration over here, which we can get to in a moment. And on the other side, we will end up with a lot of log messages telling us about the state of past jobs and current jobs. There are 4 purple squares. I've configured my machine to have 4 slaves running inside this machine. I think by default it's 1 or 2, and that's what you guys are going to have. And then there's a disk usage monitor telling me there's about 5.5 gig of disk space free there as well. If I click through to configure, and you can click through as well, you will have your node name as localhost, which is important. I'll come to that later. I've given mine a named DNS entry so it can be looked up across the network. And I've got 4 workers for mine. Is yours set at 1 by default? Yeah. 1, okay, so leave it at 1 and we'll change that later on. And then status takes us back to the status screen. So you've got 1 node and 1 worker. And I mentioned there's this difference between localhost and named host names. We'll get to that near the end. So the first task is to count the words in 357 tweets on your one machine. This is a trivial task. This is merely hundreds of lines long version of the thing we just did by hand here. So let's go to a new directory. So we need to go into to MapReduce Disco, and then I've got some more files here than you have, just because I've been doing this demo before in practice, but you're going to work up to the same set. There's a directory called tweet data, and you haven't got to go into it. I'll just show you what's in there. If I more tweets 357, which is the file we're going to use in just a moment, you'll see that there's a 357 and an 859,000 line version. So we've got 300 tweets and we've got 900,000 tweets, which will be the harder version we look at in a moment. And so all we have in this tweet list, it's a JSON-like file. So it's many lines containing a row of valid JSON, which we have to deserialize using the JSON module. And that's built into the code that we've got. And then the lines of JSON have a username and a tweet. And we're going to deal with the tweets first of all. And then if we get time, we're going to look, oh, I've got a dodgy connection. We're going to look at the social network that comes through in this as well. So if you went into the tweet data directory, just go back up 1 to Disco MapReduce. And then, so we've got 357 lines with approximately 12 words per tweet. Gives us 4,500 words to count. And many words are repeated, that's why we're counting them. So let's have a quick look at the code. So it's the count tweetwords.py that's mentioned there. So I think I've got this opened up here. So we'll have a quick review of the main file that we're going to work on. You'll see there's a line saying student to do. We're going to fill this in a moment. So that first block of code, get username tweet, that takes one of those lines of JSON and then uses the JSON module to load it. So we get 2 items, a username and a tweet, and it returns the username and tweet. So that takes care of dealing with the data format issue and bringing it back in the correct format. We have a map function down here, which calls get username tweet. And so it gets the tweeter and the tweet, so the username and the tweet back. And then we're going to do something with it. We're going to go through that process of ripping up the list of words into individual words and then counting them using a generator function in just a moment. A bit further down we have the reduce function. I'm not going to get into this, it's a little bit complicated. Basically all we're doing is taking all of the partial results from the different machines, sorting them so we have all of these lined up together, and then that KV group, key value group, we collapse the multiple counts of the into a single count of the, so we end up with the reduced count from all of the different machines. We do that on a sorted list of the iterable result that comes back from the reduce function. It doesn't matter right now how it works. All that matters is the yield line there will yield a word and the sum of all of the partial counts that came back. So if we had 10 counts of 5 each, the sum would be 50, and it would yield the word the and the count 50. And then down below we have the preamble to set this up. So here we're using one input file name, so we're giving it one file. This is important. We're passing to Disco one named file. If that file isn't visible from other machines on the network, so it's on my local host here, but it's not mapped on a network drive, then if other machines are partaking of this cluster, they can't see this data. And I've only got one file here, so we couldn't divide that between more than one worker anyway, but I can provide a list of items of data, so a list of files, but if they're not visible across the network, then other machines outside of this machine's file space wouldn't see it. But if I've got 4 workers on here and I provided a list of 4 files, they would all see the local data. But we'll get to the Disco distributed file system shortly, where we split work across the network. Ignore the import, I'll talk about that in a moment. We make a job, so job round brackets run, and we give it input, so that's the fully qualified file name, having read in the data, the map function, which we're going to complete in a moment, and the reduce function, and then we wait for it to complete, and then we iterate over the results down here, and then there's a debug line there to print. We're actually writing out a JSON file of the word counts, which we can then pass into a word cloud visualizer afterwards to see what we get back. So the first thing we're going to have to do, I should just mention this import count tweet words. When we were dealing with the parallel Pi example earlier, parallel Python, one of the points there is that when work is spread across the network, it pickles the function and the data and sends pickles of both of them across the network. Disco has to do the same. You have remote nodes waiting for work, but they don't know anything about this bit of code that we have here. So it pickles this function using its own pickler and sends the code across the network. One of the results of that is that it doesn't necessarily know which things need to be pickled up. So you explicitly tell it which modules you need. So I'm telling it, we need this module. So we need import count tweet words. And that's because the map function that's pickled for free is referring to another function inside this module. So it's referring to countTweetWords.get username tweet. If we didn't do the import, it wouldn't know to include get username tweet when it bundles that code up and sends it over the network. That'll be the first bug you encounter when you write your own code. You'll forget that, you'll assume it gets it right, it'll get it wrong, you'll get an obscure error message, and then you'll remember, hopefully, that you have to import your module.
This means I do not have to import the code myself on other machines?
Yeah.
But I have to make sure that dependencies are already there on the machine?
Dependencies have to be there. Yes, it won't package up any dependencies. So if you're using NumPy, NumPy has to be installed elsewhere. So we're going to create a generator function so that every time we call map, it gives us back a new partial result. So for every word that's in the sentence from the tweet that we are processing, we want to get back a word and a count of that word, and it's going to be the count of 1. So we found this word once, such that we can then combine those results together to get the true count later. And so we're going to use the yield keyword, which is a reasonably advanced Python way of creating a generator. So there are 2 things you have to do. You have to write some code to split the line, the tweet line, into words, and we'll do that in a moment. And then we're going to yield the count of the word and 1. And then we're going to run it, and then we'll see that MapReduce runs on our local machine. So let's go into the code. So here, student to do. We need to split up the tweet. So we can say for word in tweet.split. So tweet.split will split the tweet around white space. It's white space, not commas, not punctuation, so it's only white space. So if we have he, comma, ran, that's 1 token because there's no space in there, but he space ran becomes 2 tokens. So for word in tweet.split, and we're not changing capitalization here, which means we're going to get redundant uses of capitalization. Yield word, comma, 1. So every time we call map with a line, we're going to end, and then we're going to keep calling it, we yield each of the words that are in that line with a count of 1. Is anyone still typing? All good? So now we're going to run it. So we're going to run Python count_tweetwords.py, and it will generate MapReduce out word count for us. So we're just going to type in Python count_tweetwords.py. And then we hit return. And one job goes in, and then we get loads of verbose logging. And then it tells us that one job is done, tells us at the bottom there, and it gives us some timing information. Has everyone run that? All of you that wanted to run it? Any problems? Okay. So you should now have MapReduce word count JSON. So we can more that. More MapReduce out word count JSON. And we just see all the individual terms with a frequency after them. Many of them have got a frequency of 1 and some of them 2s. And then if we scroll through, we'll end up with lots and lots of results, some 20, some 30. These should be the most frequent in there. So that's our most simple canonical MapReduce example. So now we want to visualize the output. Oh, first of all, we should just have a look at back in the web browser. We have a job, which is green. It's completed successfully. And if we click on it, then we get some information about the job. It tells us where it was running, where the data is stored, and we get some of the logging information shown up here. So we get a handy debug output. When the job is running, it's colored yellow, and we get partial log messages, and then they fill in as it runs. So we can see it running over a network. If there's a typo in your code or you're missing data, it will typically complete either with an error or just finish because it couldn't find the data. And the typical failure mode there is that it finishes in a fraction of a second, even though you knew it should take an hour. And that normally means that you're missing data. You've mistyped your data name somewhere. So as I mentioned, we're using the local file system, so we can't distribute this across many machines. And we'll get to that in a moment. So we've made this output. We've got 1,968 lines of words. Now we want to visualize them. So this is a 357 tweets. It's a really, really trivial visualization, but it lets us see that this is working, and then we can scale up to the bigger example. Oh dear. We're going to run Python word count cloud / plot from MapReduce.py, and then I think we have to give it the file name as well. Yes, we do have to give it the file name. And so this is, I'll tell you in a moment, MapReduce, no, Python, word count cloud, plot from MapReduce, MapReduce out word count.json. So Python, word count cloud, that's a directory, plot from MapReduce. So that's taking the JSON output and translating it into the word cloud tool that I'm using, which uses scikit-learn and a few other things. And then we're giving it MapReduce out word count.json as the input file. And then we run this. For you, it won't generate a plot, but it will generate output.png. If you type EOG, which is Eye of Gnome, EOG output.png, then it will just open it up. I couldn't figure out why PIL wouldn't show an output. It worked for the MapReduce, worked for the Mandelbrot example, but not here. So this is Andreas Schreiber's really nice word count visualization. You can see that it embeds words inside words inside words, and it's really pretty. It's not terribly informative, but it does look lovely. And you can have control if you wanted to go into the code over the coloring, so you could bring some meaning into the color, but that by default it just chooses a random color. So we have some German tweets here and a couple of other tweets, not super interesting, but we get to some more interesting bits in a moment. That worked for everyone, right? So now we want to count the 859,000 tweets using one machine. So with roughly 12 words per tweet, that will be 10 million rows. And then we're going to visualize the output. I think that works on my native machine. I'm not sure you guys want to run this because it might take a little while. And I think you can run this version. It will take about 30 seconds to complete. So all you do is swap the input lines. So rather than inputting tweet data tweets 357, its input file name is tweet data tweets 859157. Those of you that are making the change, have you made the change? Okay. And then we go back and we just run Python count suite words again. And then this will take a little bit longer. So we can see up here my CPU count. This is on my host machine. So one core, we've only got one job, is doing all the work. The entries are being mapped. I think it takes 30 seconds to a minute, maybe a bit longer on this machine, I forget. In your VirtualBox, it will take a fair bit longer, might be a couple of minutes. For sure. So here we have yellow, the job is still running. When we click on it, we can see that there is one map job running and one reduce job waiting. There's only one node in the network. This is where the data is coming from. And then here are the partial results. So the entries are being mapped at the moment. 10,000, 300,000, 400,000. So it takes a little while for it to chunk through these. So in that directory you're working from, output.png should be in there. Do you see it there? But if you open up a new terminal, you should see the last output there still. So I can hear several fans now clocking up nice and high. So 700,000 entries. So what's happening here, this is the really inefficient form. So it's counting for every instance of the. It's saying, right, I've got another the, I'm going to put it on the list of these, and of another the, put it on the list of these. And the list of these is huge, the list of ofs is huge, the list of ats and a's, all of these very common English words, huge numbers that are being counted. And rather than compressing the list down to a summary list of, oh, there are 50,000 of these so far, now there are 50,001, we've just got 50,000 individual entries, which takes an awful lot of memory, which means that's a lot of data to be thrown around and a lot of memory that's being used. In fact, yeah, I think you shouldn't have been running this example because it's going to kill your virtual boxes, because we can see here that my memory is just climbing up. I'm at 6.6 gig allocated, 85%. You can see the middle chart, this one here, you can see that line going up, and it tops out. I forget how it works on your machines, so I forget this. So you might all grind to a halt in a moment. But we can get around that by making things more efficient. Let's just see, where am I at? So all my entries are reduced. And so now the final results are just being tallied up, and my memory should cut back. And so I'm finished now. You guys might want to Control C in your terminals, and we'll make a much more efficient version in just a moment. You see the memory drop off, and then there we are. Now it's back at the console. And so I could visualize this, but I'm going to wait for you guys to catch up so we can visualize it together. So how do we make this more efficient? So we've got this 10 million rows of counting, 10 million rows of single integers, and the words is a lot of memory. So we'll get to that visualization in just a moment. So we're going to do one thing here. We're going to use this combiner, this partial combiner. So it takes all the partial results in one node and just summarizes them to one count. And magically, we're going to stop using several gigs of RAM, and we're going to go back to about 100 meg of RAM, and then it will work in roughly 30 seconds on my machine, maybe a minute in your machines. So we're going to need to make this change. Have you all managed to stop your machines from running? I hope you have. It finished? Oh, it did finish. Oh, it finished without killing everything. Excellent. I never did test this example. Well, yeah, and okay. Yeah. So it's a bad way of doing things, and there's a really, really simple fix, which we'll do now. So if we go back into the code, we're going to put in from disco.func, import some combiner. So from disco.func, func, import some combiner. So that's one line. Does anyone need that up still? Okay. So from disco.func sum combiner, and then down at the job line, we're going to add in combiner equals sum combiner. Combiner equals sum combiner, just like that. And then I'm going to go back and run that at the command line, and then that's going to run in the background. So combiner equals sum combiner. So we're telling the MapReduce job to use this partial combiner. And so now it's off on my machine mapping in the background. And in the next bit, I'm just going to run through it on my machine so that we've got time to get through Minesh's next section. So you're not going to have to type any more after this. But this one should give you the partial results. Oh, it'll give you the quick results. So this is all being mapped. We look back at the memory usage and we see that there's no crazy growth in memory, but there's still only one core running, which is unfortunate. We see in the log messages that my entries are mapped. Where are we at? 100,000 reduced. What is happening with that? So new job initialized. What's happening here? I've just seen a wobble. Oh no, all finished. Okay, there we go. And then if I visualize this, same visualization exactly as before. Now it's taking the much larger result. We get that, and then we get this visualization. So I'm tweets are often about oneself. We see lots of smiley faces. It looks like a sad face, but it's actually a smiley face upside down in orange, and there's a smiley winky face. It's quite nice going through tweets. There's a typically positive attitude. It's all about me and I'm happy, and that just seems to be the message that comes through. People do rant and complain, but typically they're happy, which is quite nice. So now, in the interest of time, I'm going to whiz through this bit. Oh. Yep. So I think there's no reason, if you're just word counting, why you wouldn't use that. There's absolutely no reason why you wouldn't use that. If you're not doing word counting, then you can't use a sum combiner. You would have to make your own combiner. Yeah, yeah. If you've got a something and you're counting it, sum combiner does the partial counts. It won't do anything else. There are some other combiners, I believe, in there that help you do other things. So we've got this one item of data in one file. We really want to work in a distributed fashion. So you don't have to do this, but we can do this in the open session later if you want. I'm going to split into files of 100,000 items, the tweets 859. So I'm going to end up with about 9 files. And you see these files automatically named XAA through XAI. They have 100,000 lines each, apart from the last one, which has the remainder items. Now, DDFS, so the Disco distributed file system, we're going to chunk the work. Tweets 859157XA. Data, tweets 859157XA. So, I'm now telling DDFS to ingest these data files into a tag. So the tag refers to the data, but we've got this number of files which can be spread out over my network. Now my network is one machine, so it's all the data just on here, but now I've got multiple data files, so my 4 cores can then work on these data files in parallel rather than one core. Disco will automatically do the splitting for you on any data you put into it, but you have to have 64 meg chunks or more, and my text file is too small, so we have to do the split by hand. So we've now ingested that data. So I'm going to make a quick change to my code. So we're now using a binary format. So we need to tell Disco that we're using a binary format. So we're going to get rid of that. We're going to say input equals, what did I call this? Tag, oops. check that was the same name I gave it. Tweets 859.157.exa. Okie doke. And then down here, we need to say map reader equals chain reader. So chain reader knows about the internal binary format for DDFS. If we didn't do that, we get a Unicode-like result coming through, lots of Unicode characters that get counted. That's actually the binary format that's not been unpickled. So we're telling it to use the DDFS unpickler, effectively, and we're telling it don't use a file, instead use the tag, which tells it that it's in DDFS, and that's the name of the tag that it could be using, because we can have many tags referring to different slices on our data. And so now if I run this, couldn't find, oh, wrong thing. Can't tweet what? Oh, yeah, I'm an idiot. Right, 23 waiting, 4 running. That's the interesting difference this time. We can see 4 cores running this time, so it's going to run 4 times as fast as before, with a tiny memory hit, but there's the tiny little bump in the memory usage. So 4 running, 9 done, 14 waiting, bang, bang, bang. It chunks through much quicker this time. And if you've got multiple machines in the network, then rather than having one hard drive providing all of the data, instead we have multiple hard drives and multiple input pipes providing the data through to multiple CPUs, so we end up getting rid of a lot of the latency in processing this data. So now that's all processed, and then we get the result back. So waiting, running, reduced, none failed. And if we go back into the web browser, so this one's still running, but we can see these jobs, just as before, chunking through nicely. And so now all the partial results are coming back from these distributed work queues, which need to be reduced together. And so we're having all of these reduce operations, and then the work should just finish off. Now, I'm going to have to say, so we've talked about that already. So I've got some more visualizations that we could talk through, but in the interest of time, we're not going to cover them here and now. So we're going to cover some more of this, if you want, in the open session that we're going to hold in a couple of days' time. I've got something here to show about word frequencies. So we do a plot of word frequency versus word occurrence, and we see a massively skewed distribution. And if we plot it with a log-log formation, then it's a zip distribution that we get, which we expect for this kind of data. And then we can play with filtering the tweets. So rather than counting everything, we only count the tweets that have, for example, the word Samsung in there, so that we get only the tweets about Samsung, and we get a word count, a word cloud visualization talking about Android and iPhone. And we can use other things, so we could look at hating or loving as the word we're filtering on, and we get a really simple sentiment analysis. So only looking at tweets where someone loves something, what do they love? Or they're hating something, what do they hate? And so that's really easy to fill in, but we can talk about this in the open session. And then I've got an example dealing with, I'll just show you the output of what we do. So we're dealing with tweets. We've got people talking to other people. Were any of you in Maxim's lesson yesterday looking at social network graphs? No? Okay, so we were looking at social graph connectivity. So one of the things that we can do if we've got this kind of data is build a social connectivity graph, and then we can end up drawing a social connectivity graph using MapReduce as a method of building our graph for us, so that we can end up doing social graph connectivity analysis. So here we get a force-directed graph around all the social interactions that were occurring in this data. So this is something that we can go and explore in the open session tomorrow. Look at the social connectivity, how nodes are defined, who influences who, and how we can end up distributing these quite complicated jobs in a really simple way with MapReduce. Right, let's get rid of all of this and tidy up. There's some practical notes about machine configuration. If you're serious about using Disco, then we should chat about this tomorrow. That'll be the more sensible thing to do, I think, or whenever we run this open session. And that's the end of this. So I'm sorry for that being a slightly compressed ending. We weren't sure how long this would take and how big the class would be. So So I have to call that one to an early end and then hand you over to Minesh for his final section. Intro OS. At the end, we're going to ask you to fill in the feedback forms online as well. I believe there are links. There's a link that somebody has for us about the feedback forms. Once I figure that out, we'll do that at the end. And then via Twitter, I'll announce the open access room. And that'll be on the notice boards round near to the sign-in desks. You can. Perfect.
Okay, yes, I can hear myself. We are going to cover a third form of parallelism, and the essence of it is as follows. We have, how many of us have heard of the language or the technology Linda from Yale University? This goes back to the 80s. And the essence of this approach is you have a whiteboard, and producers are putting stuff on it, and consumers are pulling things off it. And the reason we are going to use this particular form of parallelism we'll cover next. But, okay, so this is the big picture. Let me, I guess, yeah, okay. So you have a whiteboard where the messages are posted, work is posted, and then work results are also posted. And the producers also post things, and consumers, I guess, consume the thing. And the idea here is to, of course, do this as efficiently as possible. Now, okay, so this is the form of parallelism. Now, what's the context? Why do we need it? Okay, so the problem statement is the following. We have a system, that's a function here, and it can be described in terms of, in this case, 4 parameters, A, B, C, D. And we want to find out the reply of that system in response to various values that we assign to A, B, C, D. And we are specifically interested in this case, where is it going? Well, in this case, we are interested in the value max. Okay, so we're going to iterate over all values that A can have, and B can have, and C can have, and D can have, and we're going to invoke our system, and then we are looking for the reply back, and we are interested in the maximum value returned. It could also be minimum. Now, where is the application for all this? Of course, all of us are familiar with GCC compiler, right? One can think of it as a system that happens to have 40 plus parameters. Why? Because they have 40 plus options. And each one of the options has a range of values that it can have, or low effort, high effort, medium effort. So you think of a GCC compiler as a system that has 40 parameters, each on average having 3 possible values. And you are interested in finding out, for example, I have a piece of code, and I want to find out what values I should assign to the GCC compiler so that the resulting binary is the smallest functionally correct. And there are situations where that is important. You could take the other extreme. You could have a satellite in space, and you're interested in finding out what's the best way for it to move from one position to another without it spinning out of control. And that system is made up of a bunch of parameters, and you want to simulate that ahead of time, of course. So far clear? So this is our problem. We have a system made up of a bunch of parameters, and we are interested in the maximum value returned, or the minimum value returned. Okay, so another way of stating this is to write something like this. We have for A in a particular range, B, C, D, we invoke the routine that I showed you before. That would give us the answer, right? Everybody agrees? Now, stated this way, I can simply unroll this loop. Now imagine in this case, A, B, and C, D have 3 possible values. How many times is the innermost loop invoked? 3 times 3 times 3 times 3, 81 times. Each time it is invoked, it's completely independent of any other invocation. So here we have a situation where that system func is invoked 81 times, and if we were to execute it simultaneously, they have nothing to do with each other. So what's an obvious way of parallelizing this? We covered that in today's tutorial. What's the obvious way? We know there are 81 tasks. Oh, no, a list-based parallelism, a list of tasks. We have a single list. It has 81 tasks because there are 81 invocations of this. We simply invoke it. That was the first thing that we covered. Now, why would we not use that? Any guesses as to that? Why is that not appropriate in this case? Well, for this particular example, that's fine. You should actually go with a list-based form. But if you have a system that has like 1 million parameters, imagine creating a list that is that long. The memory consumption is going to be fairly hefty. The other problem with list-based parallelism is that you have to create the list, and once it's created, it's basically done. It's frozen. You can't do anything to it until everything comes back. So it's a static concept. A list is created. You can't do anything with it until all the results come back. Right? So there are two issues with list-based parallelism. Let's look at the first form. Is there a way by which we can parallelize this without having to generate all the entries up front? That's the essence of our solution. We have a similar problem in the serial world. That's why Python has the yield statement. In other words, can we state our problem this way? So instead of generating 1 million lists up front, we're going to generate them as and when the requests come in. So in Python, that's a yield statement. Is that a fair statement, right? So if you have a bunch of workers and they're asking for work, and here I am executing this code, when a request comes in, I'm going to invoke this code, it's going to return a piece of work, I turn around and submit it to the worker. Another worker comes in, I again invoke this code, it gives him a new piece of work, I turn around and submit it to the worker. What's the advantage of this scheme? What's the overhead at the master? It's like 2 kilobytes. The time it takes, the space it takes to compile this code and save it in memory, which is extremely small. Compare 2 kilobytes of Python bytecode versus hundreds of gigabytes potentially, because you have such a long list. So this is much more efficient, right? Now, is that clear to everybody? So we have already addressed one of the issues with the list, which is that we don't want to create that list up front. We want to create it at runtime. And as a result, we generated this piece of code that is going to be invoked every time there is a request for work. Of course, there is an additional complexity of how, having to do with tracking of the maximum value returned, but you get the essence of the idea. Okay, now, but notice we played a trick here. Previously, we had a list. Now, the source of our work is a piece of code. And that piece of code is written this way. That mental jump is something we should all appreciate. Previously, it was a list of work that was submitted to some authority. And here we are submitting a piece of code that is going to be invoked by that authority. And that authority is going to visit this in this order. That's the mental jump we are making. Now, yeah.
Before it was a function call, right? Here, I mean...
Well, the function call is invoked by the workers on the other side. Whoever is being returned the value from here is going to invoke it on the other side, and you get the results back. Okay, so this is the generation of the task. Think of it as equivalent to the generation of the task, but in real time.
If there were like, many parameters, how would you list it? Like here you have the system.
Well, if there were 1 million parameters, you will have a for loop that is 1 million deep.
Somebody has to code that up, right?
Yeah. Yes. Okay, that's not good. I need your help. What tab? Okay. So now that we have a piece of code that is going to generate our work in real time, nothing says that we have to go generate work in this order. What if we could randomly go about generating work? We have that flexibility now, because the entity that is generating the work is a piece of code. It doesn't have to be range, it can be rand. We can skip things, because it's a piece of code that is generating the code now. We can say, well, I gave that job, it came back with a reply, I'm going to skip that entire parameter anymore. I'm not interested in any of the values. We have freedom that. Unlike before, now we have freedom because it's the code that is being executed in real time. That's the biggest mental jump. Okay, so what does that mean? So I have 3 animations here. And I'm going to show you visually what that means in terms of the end results. Now, in our case here, typically, although it's too bad people don't state the exact problem here. Typically, we are not interested in doing Monte Carlo simulation for 1 million entries. There is a notion of a timeout. Our manager will say, give me the best answer between now and tomorrow morning. We don't have infinite time to solve these problems. So the issue here is, okay, we are going to exploit parallelism, but there is a time constraint associated with this. Give us the best answer in 1 hour. Give us the best answer in 8 hours. Right? So there is a value to having partial answers many times. We don't have to wait till 1 month before we get the answers. So what I'm going to show you here is, imagine if our managers told us that system that we have, you are allowed to invoke it only 20 times and give me the maximum value that it returns. Don't go all the way between -3 and 3, but invoke it no more than 20 times. Why? Because you only have 20 hours. And why 20 hours? Because each invocation takes 1 hour, for example. So we have 20 hours in which we have to produce the best answer possible. Not the final answer, but the best possible answer. So this is what it would look like. I'm going to go, I invoked it 1, oops. I need to be able to move the mouse to one of those buttons and then hit.
You just want to play it, right?
No, I have to click one at a time.
Oh, right.
That's the one, yeah. Yeah. Okay.
Can we just animate it? We know that works.
Yeah.
Oh,
So,
just click on it. No. Do we? Oh my god.
is this acro read? It doesn't look like it's acro read. It has to be acro read. Open with or something. That's not acro read. Hmm. Okay. Yes. Okay, cool. Thank you. So I have 20 invocations, and I'm going to go, and I have to produce the best answer with those 20 invocations. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. If I stop here, what's the best answer? The very first one. What's the other statement I can make? I have visibility into how the system works as far as the blue region is concerned. I have no idea how it behaves beyond that point. This is grid search. You're systematically sweeping through various values that a parameter can have and trying to better understand the system. So this is grid search. Okay? If I go one more time, this is like saying if I had an infinite time, I would have seen this wave. But I don't have infinite time. I'm giving myself only 20 invocations. In those 20 invocations, I got an answer, but it is in a narrow range. Now imagine, instead of grid search, I'm going random search. I'm going all over the place. And again, I'm limiting myself to only 20 invocations. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I have an asymptotic feeling for the contours of my solution space. Of course, there are gaps, but I have a feeling for how the landscape is behaving, right? I have a sense of where the maximum, it doesn't have to be the true one, but it's certainly better than the other one. Remember, we are interested in partial answers that are as accurate as possible, because we don't have the time to go all the way to the end. If I were to go all the way to the end, it will look something like that. Random and grid, if you give them enough time, they're going to cover the entire spectrum. They're going to go about it in different order, but they're going to literally trace the entire plot. That should be clear. Right? How about if we combine the two? So I'm going to start with random. Again, 8 invocations. So I go 1, 2, 3, 4. I have a sense of where the maximum is. I'm going to switch to grid search around the maximum region. I go blue 4. 1, 2, 3, 4, 5, 6, 7. What happened here is I went with random to get a better sense of the landscape, zoom in on the region that is of interest, and then do a more accurate grid sweep. Now this is just one parameter. Imagine if it's a million parameters. It's staggering how much work is being done that is useless by treating that we have to go through the entire thing to get the answer. Imagine if we had the ability to mix these two in a fault-tolerant, efficient manner. We'll get not the accurate answer, but a good enough one. It's an estimate. Everything is an estimate. So it's not enough to say we want to exploit parallelism. We want to exploit parallelism given certain deadlines. Right? I've noticed that if you have a problem that takes a month on a serial machine, and you bring it down to a week, people appreciate that. From 1 month to 1 week. But if you bring it down to 2 weeks, they say, big deal. It's that 1 week that is mentally special. If you go from 1 week to 1 day, that's special. If you go to 2 days, from 1 week to 2 days, they are not interested. If you go from 1 day to overnight, that's like premium, because everybody's sleeping and the thing is working. That's the next value in the speed up that is valued. And then when you go from midnight to lunchtime is the next speed up that is valued. Anything in between, they don't give a damn. So not all speed ups are valued equally. Month to week, week to 1 day to overnight, overnight to lunch, lunch to real time. It's not a continuous function, it's a step function. It is in that context that this makes sense. Okay, so of course, if I were to let it go all the way to the end, you'll end up with the same answer. The question is, how many iterations does it take to get to that without having to go through the whole thing? Everybody clear on that? Okay, so now onto the code. I don't need this anymore. Man, I'm really lost here without my laptop. Okay. Good God. No. I need to go to the prompt. Seems like something is running.
You want the virtual box now?
Yeah. Oh yeah, okay. Thank you. He's in UK, I'm in Mountain View. We made sure each other's things worked, but of course, my hotkeys are very special for me. I'm lost without them. Okay. Yeah, there should be no British keyboard. There should be only American keyboard. That's it. We go with grid first. So this is a case where again we are going through the grid search, and we are interested in finding out the values, the maximum value returned, and we are going to use the scikit package from Python. And the reason for that is because they have implemented the grid search implementation. Okay. So if we just invoke that, it's going to do a bunch of things. It's reading some data, and it's now about to launch a couple of parallel jobs and try to figure out, given a particular set of parameters and those parameters are listed there, CLF, alpha, penalty, max DF, and max N, and the values are written over there, right? So in some cases, it's the floats that are provided as ranges. In the second case, you can see it's a string. So GCC as a system is what? Strings. GCC does not, and none of the options for GCC except a float, I believe. They're all discrete. So here's a system that has float values as well as discrete values. And we're interested in finding out the best answer. Now what I've done, I think, yeah, it's going to go through a series of jobs and then finally report an answer. We should be almost there. Okay, there, it's almost done. So 72 out of 72 jobs, and this is the best parameter set that was returned for that particular equation. But it went through the whole sweep. Okay? So if you have a system that has 1 million parameters, this is going to take a long time. It does use parallelism in the back end because you see parallel jobs there. But it's all set up for just the laptop. I didn't go through the trouble of setting up for multi-machines. I believe it does support, but I'm not sure. Everybody get this? In terms of the code, a bit about the structure before we even talk about that. Of course, I'm in this directory, 3HPO. And there is a file called session that gives you the output that I generated when I ran a couple of weeks ago. So in case you are sure or kind of curious about how things work, it shows you the actual dump. And of course, that is session. The utility function, because I'm going to cover random search next, and it depends on MongoDB for the database. Remember we told you that there is a whiteboard there. So for random search, that particular implementation, which is an open source package, relies on MongoDB for the whiteboard concept. While in the other case, it's actual Python code. So rather than having to say to you, oh, I'll open up 4 windows and have a Mango server here and daemons here and all that, there's a utility directory where all this thing is basically automatically spawned. Now if you're interested, you can have a look at it. Oh my God, this is bad. Okay, so it basically just invokes the masters, cleans up the machines and all that. Because one of the things with these demos, especially with MongoDB, is if you're not careful, it will automatically generate a database of a couple of gigabytes, even if you're playing around with it. And this thing will literally crash. So there are a couple of subtleties that I had to take care of. But if you don't mind all that, you can simply skip over this. Cancel. Oh my. Where is Emacs? World without Emacs is not good. Okay. Okay, I'm going to go back up. Okay, so let's look into gedit and search random. It's an easier piece of code. And we'll go back to grid next. So random search. And notice what I'm doing here. I purposely, what I did not have enough time to strip down everything because I wanted the demo to focus on the essence of the matter, not all the logistics of, oh, set this up, set that up. So this is what is reflected here. I have a function that I'm trying to minimize, and in this case it's a sine equation, the one that we saw before. And it's going to be invoked by providing the value x, right? And we are interested in returning that value. And I'm putting that scan in here because I want to generate a plot. It may be hackish, but for now it will do. But if you're not interested in the plot, you don't need the scan as a global variable. Simply compute it, and that's basically this function right here. This fx is our function that we described previously as a system. And here it's a function of just one parameter. And so the first thing we're going to do is, of course, invoke the open source package. It's called hyperopt. And that particular method, which is fmain, and we are telling it this is the function I want you to scan over, and this is the range for the solution space, which is between -3 and 3. We are interested in finding out the values for sine equation, and we are interested in using the serial version of it. That's what trials is, and the algorithm with which to go about it. And this is suggestion, which is a variation of random. And the maximum evaluations here are 60. Of course, in my animation, the value was what? 20, right? And then I go ahead and I print the best value returned. So for 60 invocations, it will give me the best value. And the rest of the code is simply plotting that stuff onto the screen. And this is a way to see the thing randomly. Well, one of the interesting things about machine learning is sometimes the data produced is so far removed from what is going on under the system that this kind of a capability helps out. We can see visually what is going on, so we have a sense of where the bottlenecks are. And so this previous version was a serial one running on the machine. And the next version, I'm going to spawn 2 workers. I'm going to use the same open source package, but I'm going to tell it to talk to the MongoDB to post and require work from, and not process it internally. So for that, I need to set up the MongoDB database. And the next thing is I invoke the same function as before, but I'm using a different target, which is this one, MongoDB, as opposed to the local piece of code. And again, I'm invoking 60 times. Of course, the answer should be the same. Although it's random, you're repeating the same thing over and over again, right? It's pseudo-random. And finally, I terminate. The reason to write this method is because once Mongo is created, it tends to hang around. So this is a way to make sure everything is cleaned up. But you don't have to pay attention to that. If it's a kind of a standard package, there's no need to terminate the DB. It will cause headaches for other people. We are back to this being very moody. No, there is one section I have to run invokes a random search. Okay, cool. So now we say Python search random, just like before, we're using a different scheme, and you see what is happening here. The values are generated, and I'm kind of simulating how they are generated, the order they are generated. And of course, there are 60 dots because there's 60 invocations. And it will, after that, which is the first phase, which was serial, next thing is to redo the same thing, but using multiple machines or multiple processes. And that's what's going on in the background. So if I just shut this for now, it will take some time. But notice the value to return, saying that for value of x equal to minus 1.5 is where there is a maximum associated with the system. And after some time, we'll have the workers report pretty much the same answer. Let's go. This is interesting. Okay, we can kill it. We can start search again. Gedit search random. Give me an example of a simple system that you can think of. Anybody? We have sine equation here, right? Give me an example of a simple equation that captures our system. Cosine x times 100 divided by what? 4.7. And right here we created another system. And we are going to go in and we are going to save it, coming here, invoke it again. Gedit. We need cosine. We come here. Sorry? Thank you. Thank you. Cosine. Save. Come here. And what do we manage to just do? We change the very system. Look at the value returned. It's completely different. And look at the value, the things that are plotted. Of course, it's outside of this range. That's why we don't see hardly any plots. I said plus 110, right? Maybe I shouldn't be that aggressive. But you get the idea. What did it take me to change the system? I went from sine x to some other equation. It doesn't even, that equation doesn't even have to be written in Python. That callback that we called to be invoked by the system. Let's pretend to be in a situation where we are trying to simulate an entire satellite, and we have a complicated simulation written in C++, for example, for that satellite. Now, how would we simulate such a system with this kind of a code? Simple. We go to this function here, and instead of writing this code in Python, we actually turn around and launch a co-process and say, launch my satellite simulation with this parameter and come back with a reply. And off you go, and the rest of the mechanism is in place. Does that make sense? So here you have a situation where this piece of code doesn't need to be written in Python. It's encapsulated by the actual application sitting outside. And yet this mechanism will be able to invoke it, collect the results, and off you come back with the answers. Now, is that clear to everybody? Right? Okay. The next question to answer is, we mentioned in our communication, when we define what parallelism is all about, this notion that there is a notion of a toxic communication primitive that if used will result in problems. Can you think of any situation, an example of a toxic communication in this context? Something that if it's used, it's going to cause problems. First of all, what is the communication primitive that is safe in this context? The only thing that is safe is between the producers and consumers and the whiteboard. Right? That's the one that we are using here. Producer pushes things, producers push and produce, and consumers are doing the same thing. That's the only communication primitive that is being used here. Is that clear? Now, give an example of a communication primitive that is invalid, that is toxic. That if you were to use, it's almost guaranteed you're going to have problems. No, that's a blockage. That's a deadlock. This is like weird behaviors, premature terminations, and deadlocks for other kinds of reasons. So one example of a toxic thing is that the workers who are supposed to talk to the whiteboard, behind their back, are talking among themselves. Meanwhile, the producer on the front end is not aware of those things. And when one of the workers goes down, the other work is waiting for a reply, and they're never going to get it. Because the manager on top is not even aware of those things. It's going about conducting the whiteboard business, assuming everybody's coming in and going out. So here you have a situation where the workers are talking among themselves in a way that contradicts the policies by which the manager is going about doing its work. Whenever you have that, you have a deadlock. It may not be 100% of the time, but it will be there. Now, the other thing to note about these things, about the deadlocks, which is because of misuse, the tendency is to say, well, let's file a bug, saying that these workers were communicating among themselves, and in that context, this thing hung, and this is the stack trace. Now, let's say we are the authors of that package, and we got that bug. What is our first response? We're going to try to fix it. This is a special bug. It cannot be fixed. When you have a whiteboard, the other communication primitives have to be disabled. If they are used, you will never be able to fix it, no matter how hard you try. So if you treat these bugs as ordinary bugs, you're going to waste a lot of time thinking there's a light at the end of the tunnel. There is no light there. You will never be able to fix it. And we're going to experience this over and over again, all kinds of situations going forward. Questions? Yeah.
I'm wondering, how would you model, that the workers are communicating with each other and the manager does not know that they are communicating with each other? How would you model that?
Well, the way we model it is actually patented, but that's the way we do it. What we do is we have the manager that says, here is a piece of work you're supposed to execute, but here is also the bit vector of all the communication primitives you're supposed to use. If you use anything invalid, we are going to terminate you in situ without coordinating with anybody. And we're going to produce a stack trace saying that you did something invalid. We are not going to allow you to proceed. So in that context, a worker is given a piece of work saying, go talk to the whiteboard. The worker then turns around and launches some open source, or it doesn't have to be open source, some module that does a really good job, not knowing that under the hood, that communication is talking to other workers. When the worker was given that piece of work, it was given not just that piece of work, but the bit vector of all the communication primitives that it's allowed to use. Unknown to that caller, this other module is calling send receive. It's going to be tracked right there, saying you're not allowed to use it. You don't have that, you have all these deadlocks being reported, and there's an attempt to fix it. They are all going to fail. Same thing with parallel data structures. Whiteboard, the way it is designed, has a specific pattern. Things are coming in, things are going out. Right? With parallel data structures, it's the same thing. You can think of a whiteboard as a parallel data structure. Why not? But it has a specific communication primitive that is safe. Anything outside of it is invalid. You can have other kinds of data structures that have other kinds of patterns. It's the same principle. Okay, otherwise I'm done. Yeah, done.
Well,
so we have 5 minutes. Would really appreciate if you could take the time to fill out the surveys, both for the tutorial community as well as the two of us. There's a we have to twist our way 20 ways from here to Sunday to express an obvious idea. If it's too much freedom, we're going to be overwhelmed with too many choices. So this vocabulary has to be just right, and that matters. Okay, so before we define parallelism, now that we have the big structure, homage to a frequently asked question on the web on this topic of parallelism, and that is this: is exploiting parallelism easy or hard? Right? Now, I don't have a blog, but if I were interested in having a blog and generating a lot of traffic with the least amount of effort, given that I'm fairly lazy, all I have to do is answer this question. Pose the question, answer it, sprinkle it at Hacker News and a couple of other places, and hordes of people will show up. There's something about this question that just attracts people. And yet I'm not a fan of this question because it's an absolutely toxic question. And the reason is, somebody were to pose this question to me, I just have to say yes or no. I don't have to bother to justify my answer. And so what ends up happening is there are dime a dozen opinions on this, and therefore a lot of noise. However, I'm fascinated by this question, because we know from situations, on our own experience, there are situations where parallelism is extremely easy. Even if it involved two machines, who cares? It was easy. And then in the rest of the situations, man, it's so painful. Now the question is, why is that the case? To what can we attribute this degree of difficulty to? Right? In today's tutorial, we're going to talk about 3 forms of parallelism. Why 3? How should you decide which one to pick? And turns out that the essence, now I'm not claiming that if you answer this question, we have solved all our problems. What I'm claiming is that it helps us establish constraints within which we have to operate. So the other engineering fields, the electrical engineers and the structural engineers, they have a nature to keep them honest because they have physical laws that they have to follow. With software engineering, it seems like anything can go. This is like an analogy to that. We have to follow these guiding principles. So what's the answer? Why is it something difficult and something so easy? Everything has to do with one simple thing, which is the gap between the intent and the API of parallel enabling technologies. If the gap is large, the project is going to be tough. It doesn't matter what language you use, it doesn't matter what the infrastructure you have. If the gap is small, it's going to be a piece of cake. So if somebody were to tell, for example, consider an analogy. If somebody were to tell me to build a wall somewhere here, I could build it 1 grain of sand and clay and cement at a time. And just thinking about it gives me a headache. Or I could take a break and say, I'm going to introduce a notion of a brick. I'm going to use bricks to build a wall. Now, what is the difference between the API of the brick and the API of a grain of sand? The API of the brick is closer to us in the context of this wall. That's why it makes us efficient. API of the grain of sand is much further out. So if we have a gap, that gap has to be bridged by us, the software engineers or the domain experts, not the provider of the brick and not the provider of the grain of sand. It's our responsibility to bridge that gap. So the model here is we want to always, so the essence of tying back to the solution here is talking about the vocabulary. If I'm thinking in terms of MapReduce, I want the runtime environment to give me the ability to express MapReduce. If I'm thinking in terms of a list of tasks, I want the same environment to give me the ability to express a list of tasks. I don't want to find myself in a situation where I'm thinking in terms of A and the system only provides me B, and then I have to kind of map my way from A to B. If I'm thinking in terms of a template, the system has to allow me to express the notion of a template. That's the only way we'll be productive with parallelism. There's no other shortcut. So if that is the case, then the natural question is, well, how many types of PETs are there? Seems like it's very important. It kind of determines whether we are going to be successful on a particular project or not. One side note, the most important attribute anybody can bring to the table here when working in this space is knowing what to avoid. There are simply too many choices here. Right? That's the most important attribute. Whether you're a domain expert or a software engineer, you need to know what to avoid. So what are the, sorry, yes? And I'll get you in the very next slide, the one that I was about to click to. Okay, so the PETs now. How many types of PETs are there? Because they determine how far off we are from our notion of parallelism. There are three kinds. The first ones are libraries. So you have OpenMPIs, OpenMPs, and the CUDAs of the world. They come at us from the perspective of the respective hardware systems. So OpenMPI was created 20 plus years ago to express parallelism across servers. OpenMP came about because of the need to express parallelism inside a node or inside a server using only control-centric nodes or control-centric threads or cores. CUDA came about because of the need to express parallelism inside NVIDIA's GPU cards. They are all coming at us from the respective hardware systems. Meanwhile, we are coming at the same problem from the other direction, with the perspective of a particular problem. That gap has to be bridged, depicted here in green. And today and going forward, we cannot use just one form of parallelism. We need at least two, because we need to keep the local machines busy and multiple machines busy. So we are talking about using two very different libraries that have two very different ways of interacting with us. They have their own conventions, their own vocabulary. We have to somehow manage that on every single project we use. So this is literally like building a wall one grain of sand at a time. Really powerful, but we have to be careful. The second approach is completely opposite, taken by frameworks. And the way the frameworks work is that you look at the entire landscape and you pick a thin slice of the landscape and you take complete control over everything inside that landscape. And you turn around and say to the developer, if you want to solve anything in this problem, in this space, break down your problem in terms of map and reduce. Give me those two callbacks and I'll take care of everything else. That's what, those are what frameworks bring to the table. They tell us, the developers, give me callback for map, give me callback for reduce, and I'll take care of everything else. This is great, provided I can break my problem into map and reduce. If I cannot use it. I have to use some other framework which has its own vocabulary, its own way of doing things. So this is like Model T in any color as long as it's black. If you like black, it's fine. If not, you can't use it. But there is merit to this approach, right? Because it does close the intent, the gap between intent and the API. It's just too restrictive. The vocabulary is not rich enough. It works in one situation and not other situations. Which brings me to the last environment, which is self-contained runtime environments. Now, in the interest of, there's an echo here. In the interest of disclosure, my company's product is the only one in this category, but put that aside. What do self-contained environments bring to the table? The ability to say, I want you to execute DAG right now. It will morph itself so that it can process DAG in parallel. When it's done, it becomes neutral. I turn around and say, now execute a list. It will morph itself so that it can process a list in parallel. And when it's done, it becomes neutral. So now all of a sudden, I have a single installation, a single binary that can be used to express multiple different forms of parallelism using the same vocabulary. Right? So that's what runtime environments bring to the table. Okay. Now, the cool thing about our definition of parallelism is that regardless of which approach you take, our definition of parallelism will work. At least I don't know of any exception. And the essence of our definition is just 6 words. When we have this kind of a situation, is we have to answer the question, how are we going to manage the execution of these things? What does it mean to successfully finish? How do we handle premature terminations? What is the fault tolerance policy? How are we going to handle deadlocks? If we have answers for those things, the resulting software is going to be really robust. If we don't, there is a price to be paid. And it's fairly hefty. It doesn't really matter which language we use. It is what it is. Okay, so now there are various ways of answering this question of how we manage this. We could write a documentation that says when you launch these jobs, use this script. When it finishes, use this other script, and on it goes. Or we could have a website that shows us the jobs that are submitted, that are running, that are finished. Or we could hook it up to an email system that says, oh, this job is still running. Or we could have a hack, which basically pings the system saying, I submitted 2 jobs an hour ago. Are they done yet? Are they done yet? Are they done yet? What if we could actually write a parallel module? An honest-to-goodness software that just works. Now, if we could do that, then all of a sudden, we can invoke these multiple modules. We don't have to second guess. We don't have to check our emails. We don't have to check the website. I can tell the module saying, I don't care when you start, finish by 8 o'clock tomorrow morning. It will finish. What if we could write that? So imagine a world where that is possible. This carries on for some time until someday we realize we would like to have multiple invocations of the parallel module itself. Our system is getting larger. And just like before, whenever you have multiple things going on, you have to answer the question, how are you going to manage those executions? And just like before, you have choice. You can have documentation, you can have a website, you can have a hack, or how about if we write a program, an honest-to-goodness program that allows us to exactly describe what this parallel workflow is going to be, and it will always work. It will never hang. This carries on until one day we realize that our competition is solving a problem that uses only 10 machines, and we are using 1,000 machines for the same problem. So we have an issue now. How are they able to get away with only 10 machines? So we are going to now go into our workflow and come up with various versions of various capabilities. So instead of using a GPU, we'll use something else. And in other words, we have various incarnations of our workflows. And the story repeats again. Whenever you have multiple things, you must answer, how are you going to manage? So to tie this to today's presentation, we are going to have 3 forms of parallelism, which means that we have 3 ways by which to manage resources. Okay? Now, this is the part of the story where we can't go any further until we define what parallelism is, notwithstanding the footnote. So, but before we get to the footnote, I want to, how do we write this parallel module? How do we write this parallel workflow that it just works? We need some guiding principles that kind of help us along the way. And this is the most powerful quote that I can think of. It's really profound. I can't say enough good things about it. It's by Benjamin Wolf, who said, a language determines the concepts we can think of. Now, this was in the context of, he's a linguist, or was a linguist. So this is in the context of languages, human languages. Now, when he made this statement, it was fairly controversial. I don't understand the controversy, because anybody who's been taught multiple languages from childhood knows that there are certain languages that are really good at something and not others. So we'll take this as a given. Languages determine the concepts we can think of, especially for parallelism. Boy, does it make a difference. But we have to augment it for our situation. So we're going to say it's not just a language that determines the concepts we can think of. Runtime environments determine the concepts we can think of. Parallel frameworks determine the concepts we can think of. And so do parallel libraries. They all bring unique set of vocabularies to the table that allow us to express parallelism. If they're too restrictive, parallelism is all about the management of a collection of serial tasks. Begin and end of story. Any parallel capability must have three parts. A notion of a manager, not a scheduler, manager. Manager has to schedule and do other things. It must have a notion of a serial task, and it must have notions of communication primitives. The manager has to enable and disable communication primitives. Now that may seem really odd, but we will see ramifications of it. And of course it has to do scheduling, which I'm sure all of us are familiar with. Again, what it means for today's tutorial is we have three forms of parallelism. So therefore we have three ways by which to manage things. So therefore we will have three very different sets of policies. Serial tasks come in two flavors, coarse grain and fine grain. Everybody knows what this means, right? Coarse grain, fine grain. Anybody? Any issues here? You run GCC compiler 1,000 of those things on 100 machines, that's coarse grain. Because there is no need for the individual task to communicate until the very end. If you need to communicate before you conclude, that's fine grain. So this is what parallelism is. It defines what goes inside a GPU card, inside Intel's mic, x86 cores, and inside servers. So again, to summarize, what management policies focus on is how the serial tasks are managed, not what they may be doing. So in our examples, the examples are written with certain things in mind. You can certainly go home and change the notion of a serial task, and the rest of the examples will continue to work. This is the reason why it does. And this is nice, because I'm no longer pitching in the dark. There was a very nice report issued by the National Academy of Sciences late 2011. It's a report that explains the entire history, past, present, and future, and it acknowledges, this is a direct quote from them. But the mysterious thing is, they mention this, but there's no one section on it, there's not a page on it, there's not a chapter on it. They acknowledge it and then they don't build on it. No matter, we'll take credit from anywhere. Or not credit, but validation. Okay, so now we have defined what parallelism is. Let's go, this is the essence. Think of the big picture. Don't think in low-level details. Of course, there's no free lunch here. Right? All of us are able to drive a car without knowing anything about the gearbox or the transmission or the engine. That doesn't make us stupid. It allows us to do other things. So with parallelism, if I'm able to express parallelism at a higher level, let the equivalent of a mechanical engineer worry about the low-level details. Imagine the world where in the morning when you want to start the car, there's a spec that says you have to be a mechanical engineer before you can even start the car. We'd be lucky if we had like 50,000 drivers in the world. The reason we are able to drive a car is because it protects us from the dashboard, protects us from the low-level details. What we want is when we exploit in parallelism, we want the equivalent of dashboards. Not everybody needs to work in the low-level details, and certainly not the domain experts. Okay, so here's an example. I'm trying to do my level best to give you examples of actual Python code. So here's a typical example of a serial module where I have a serial task. The one thing to note about this is not the content, but the fact that the serial task is a function of the arguments. If it's a function of the arguments, if I invoke it 100,000 times, they're going to work on 100,000 different things. So that's one very important thing to recognize. Right? Everything inside the body is a function of those arguments. If that is the case, we can invoke it multiple times with different arguments, at least in this case. Here's another serial algorithm. This is a slightly different one, and what I have here, you see this rank D. It's basically a rank order. It's given a unique ID. I can use it to create all kinds of temporary scratch pads and things like that. Okay, so a few words on, this is rather loud, no? A few words on my bio. I spent 8 years developing enterprise software, both serial and parallel versions that are still used by hardware engineers to manufacture and test their chips. So chances are the chips in your laptop or cell phones were designed with that software in mind. And since 2006, I've been on my own self-funded engineer, CTO. We have a complete SPM Python, which is a distribution for high-performance parallelism, and a consulting angle. So anyway, a footnote on the topic, on on this general term of exploiting parallelism before I go to the main topic. And that is this. This is the year 2013. Okay? This is a field that is at least 60 years old, 60. And yet there is no consensus on what this means across the open source, academic, and commercial world. So if you gather 5 experts and you ask them, well, what does this mean? You're not going to end up with 1 or 5 answers. You're going to end up with 30, 40 answers. I can't think of any other field that is 60, 70 years old that has this issue. It's really damning. So in light of that, what I'm about to say, you may by all means consider it suppositions on my part. Totally fine with me. We'll be making quite a few very strong claims. So, okay, now the topic at hand. Now I'm sure all of us have come across some version of this plot. And what I have here on the x-axis is the size of input, which can take one of several forms: data, graphs, and matrices, sparse and dense. And then on the x-axis, of course, there is time. And this is the situation that we face. It's basically growing on us, right? So far, no surprises. Things to note about this slide, specifically things that are not mentioned. There's no reference to big data. There's no reference to smart data. There's no reference to data with depth. And just to pick on big data, if what we face can be attributed to big data, my question is, what are we going to call it tomorrow? Huge data? And then what? Humongous data? So I, for one, am not interested in tracking this nomenclature. There are enough real problems here that we don't need a buzzword-centric take on things. So the real question is, what are we going to do in response to this? That's where things get very interesting. So let's come up with an answer. It turns out the answer can actually fit on a single slide. The essence of the solution will work no matter where you are along the plot. Tens of megabytes, gigabytes, terabytes, makes no difference. And we're going to derive that answer through a series of transformations. And to start that off, let's imagine that we are in the recent past, where this was a typical situation. Where we'll be invoking some serial module. It will be CPU bounded. The emphasis here is on parallelism, not concurrency. How many of us have heard of those two terms, parallelism and concurrency? People misuse them, so I just want to emphasize that it's parallelism, not concurrency. So we have a serial module, and we were invoking it, and then after some time, we would have realized that wouldn't it be nice if we could invoke multiple instances of the serial module with different parameters, for example. And so we would essentially like to do something like this. We would like to have multiple invocations of a serial module. Now, just like in life, anytime you have multiple things going on, there must be a notion of a manager. So the first thing we have to do when we are